Welcome everyone to our final session of the Data Science Summer School 2023. My name is Hui Dang, and I'm the manager at our Data Science Lab here at the Hertie School. In case this is your first time joining us, the Data Science Summer School is our annual effort to contribute to the open source communities by opening up scientific learning for the general public. And we're very happy to see that you have decided to spend some of your precious summertime with us today. And our summer school is made possible by the generous funding of the Hertie School and the Dietrich Foundation in Germany. And I'd like to thank them for their continuing support for the organizations of the summer school. Our session today is deep learning for multimodal systems. And the session will be led by Professor Christian Arnold. Chris is a senior lecturer at Cardiff University. Using data-driven methods from statistics and machine learning, his work lies at the intersections between social science and computer science. And his substantive research focuses on institutions and governance, what drives and determines the rules of political decision-making. And prior to joining Cardiff, he also had positions at Oxford University, and he also worked as a data scientist in the industry sector. He graduated with a PhD in political science from the Graduate School of University of Mannheim. And Chris, the floor is now yours. I hope everyone will enjoy the session today. Thank you very much.
Thanks, Hui. Hello, everyone. Really good to see you. Welcome to this journey. Let me share, like as a bit of, let me share you my screen, and I think we'll just take it from there. Okay, so welcome to this session on multimodal learning systems. Let's start with some logistics first. Everything we will talk about is on my GitHub repo, and it's Chris G.U. Arnold, and then ds3_multimodal deep learning MMDL. And you can find the links to the Google Colab code that we're going to use later. It also has the slides, so everything you need will be there. And that's sort of your go-to place for the whole session or for checking it out afterwards. I'm really excited to be here with you guys. This is really, really cool. As Hui already mentioned, thanks for spending your time with us here. And this is an exciting day. I hope for you guys to get a first primer into what multimodal data means, how we can analyze it, what the challenges are, and also what the opportunities in there are. In case you have any questions, always feel free to ask them in the chat. Hui will handle them. Also feel free to and feel free to unmute yourself in case you want to ask them instead of like in video, instead of typing them. Since I'm sort of full screen here, I probably won't always see them, but Hui will remind me if I'm missing out on something. Okay, so please do ask questions. We will handle them as a team, and then I can respond to them as on the go. Since it's a 4-hour session, it of course makes sense to ask them on the go. And at the end, we will have some dedicated time for discussion as well, in case there are sort of larger questions that are left over, of course. I really want this, even though this is quite a sort of a lecture style session, I guess, I really want this to be as interactive as it probably could be, right? I mean, we all got used to this setting where stuff is virtual. Just to give you an idea on my end, right, I'm staring at a screen with a lot of people without their videos on, which is fine. So I'm talking into a black hole, and I hope everything is fine, and that you're all sort of managing to get along with what I want to explain. So as mentioned, if there are any questions, don't hesitate to ask them. We'll get to them. So a little bit about my own personal background. To me, this is the most exciting time to be a social scientist in like ever. And this is the only reason why I am in science and not earning a lot of money happily as a consultant, because I really, really believe and know that this is the most exciting time to be a social scientist. And I can give you the reason for that. The reason is quite simple. First, we have a lot of data that 20 years ago we did not have. Okay, so this is think about all the sensors that we are wearing on us every day, right? We have smartwatches, we have a smartphone, and just these two devices are collecting data at an unprecedented level. Right? There are whole countries who are building, quite elaborate systems to monitor populations. And those countries collect a lot of data. Companies collect a lot of data on us and want to sort of try to make the most of us as consumers. So for the better, for the worse, we are collecting a lot of data about individuals and about society. That was not possible just, I don't know, 25 years ago, when probably most of you were born, roughly. Back in those days in the 90s or before that, if you wanted to do social science, the only way to get to data was basically to, I don't know, field a survey or get people into your lab and then ask them questions or have them fill out stuff, do experiments then. And this was basically the only way. And now we really have so much observational data. This is really exciting. Second, we have those computers that we can actually use in order to make sense of all that data and of all that information, which is pretty cool. And lastly, we also have the tools that get better and better. All the algorithms that we have, not only just statistical models, but also tools from machine learning and that are available to us as social scientists. They are pretty awesome. And if you've ever played around with large language models like ChatGPT, for example, or the stuff behind ChatGPT, you will have an idea of how you can actually make use of these modern technologies in order to analyze your data, to mine your data. This is really, really cool. So the only reason why I'm doing this job is because it's so exciting to be a social scientist. And I think this is unprecedented. I'm completely overwhelmed. This is my very reason to be in this business and also to teach this course, because I think the stuff we talk about today, multimodal learning, is the next step in social science, where we can discover new opportunities for modeling what is challenging data, but it's very promising and we can get a lot of information out of this. So we already mentioned quite a number of things about myself. I am based in Cardiff University. I have a PhD from Mannheim University. I do research actively using multimodal deep learning. One of them is to detect voting fraud. There we mix data streams from satellite, so remote sensing data, with microdata, so population data that is geographically located. And that's a form of multimodal learning, right? You have two different data streams that describe the same thing, and that's multimodal learning. Another one is more classical, or what you might have known as multimodal learning already, is elite communication. So we study basically the three modalities that come from a person that you are watching, right? Like in this very video, you listen to an audio stream. So you have different audio things going on. You have text that can be transcribed from that video, from that audio stream, and you have the video data. And this is a classical trias, and we are analyzing political communication in that context. In the very end of today, when we talk about alignment, I'll showcase you some of the stuff that we're doing. Also, one of the reasons is to give you an idea what people currently do in political science research. I have an industry background as well, a little bit. So I worked as a data scientist for some time, and consultant in that area. Worked a bit with the ONS and with the National Democratic Institute with NDI. we help them to improve their technology stack to detect voting fraud in the field with the help of data science. So this is me. Ideally, I would have the time to get to know you, but simply because you here in the Zoom, and then people even out there on YouTube who could not make it into this very room, we can't take a quick tour de force through everybody, unfortunately, since we are too many here. But I'm assuming a couple of things about you, and this is sort of how I designed this workshop, hoping that it pitches the correct level of knowledge. So I am assuming that you all have background mostly in social sciences, be it, I don't know, business administration, psychology, anthropology, political science, economics, whatever. So you are probably used to a more kind of a regression framework when you think about data analysis. I'm assuming a kind of, even though you have the statistical background, you had contact with machine learning already. So you know how machine learning works, how to do it properly. And you probably also know R and Python or R or Python in order to do things. Today, when I show you code, we will use R, since this seems to be more mainstream in social sciences still, and less people know Python. But everything we do in R today, you can of course do it in Python, right? That's not a big problem. I'm also assuming that at the moment you are pursuing a postgraduate qualification, so a master's program, a PhD, or a postdoc or something, and that you're not undergraduates, simply so that that's sort of the kind of level that I'm pitching to, and I hope that this works for everybody. I also assume that you had some experience with deep neural networks, and I'm not assuming that you're an expert data scientist, but I'm assuming that you did have some basic exposure and played around with this already. So you know how recurrent neural networks work, how convolutional neural networks work, and all these things. We'll go through deep neural networks quickly in the beginning. But this is really meant as a refresher. I know from Hui and from the last years that there are some really excellent introductions into deep learning that have been going on here in this DS3 space, be it on convolutional learning, convolutional neural nets like computer vision, but also NLP, some basic introduction into neural networks. There was a part from on generative adversarial networks to synthesize data. So there is a lot of groundwork that you can find easily on YouTube in case you are struggling a bit with the foundations. But I'm assuming that I can build on top of this knowledge here in this module. Okay. So what's in the package? What's in today's agenda? We will talk about. We will have an introduction. This is where we're at, right? Then we will lay some foundations, and that's mostly refresher stuff, thinking about what multimodality actually means and all these things. I think we'll spend roughly 90 minutes on the introduction and foundations overall together, a bit less. We will then go on to take a look at the basics of multimodal learning. What does it actually mean to do multimodal learning? And then in the afternoon, spend some very good time on some extensions, particular representation fusion, representation coordination, and the alignment of multimodalities. Overall, we will have, and this is my insight from pandemic and lecturing online in different contexts, we will have two large chunks. Okay, so we will go until 12 o'clock Berlin time, and then have a 15-minute break, 1-5. And then regather for another 2 hours in the afternoon Berlin time. And during those two hour slots, we will have 2 5-minute breaks each, where I encourage you to get up, stretch, have some water, do some logistics, get some food, whatever you need. But yeah, so we'll have a couple of, like in the morning, we're going to have 3 sprints, and in the afternoon, another 3 sprints with 5 minutes breaks in between. And this apparently worked pretty well. That's my insight from the pandemic. So what are today's learnings? These are the 4 sections that we're going to tackle. This is whether it relies, whether it builds your knowledge, whether it builds your sort of experience. And by that, I mean some kind of intuition for what is going on, and practical, like viewing things, not just the theory of it, but also getting an idea and the sense of applications. And then skill is really learning to code in our context, right? Doing the maths, not so much, but much more, can I actually do code and do things? The introduction and the foundations are, of course, more knowledge focused. Then basic multimodal learning. This is really the heavy hitter, and this is why those axes are in bold here. So I'll properly introduce you to what it means to do multimodal learning. I want to show you some examples of multimodal learning, since I'm a political scientist, from papers in political science. And we will cover some code in that area as well, so that you can go home and actually run models on your own. When it comes to the extensions, we will again be quite heavily focused on the theory here. And I'll also show you some examples on stuff that you can then do with those extensions. But this is a bit more advanced stuff, and to dig deeper into those extensions, we would have had to have another full day at least. Yeah, but I think overall this is sort of the package that we're going to cover all together. Okay, if there are no questions so far.
Yes, questions.
Cool. Then let's just dive in right away, okay? Yeah, foundations, deep learning. This is a refresher on deep learning, very briefly, okay? We're going to cover it over the course of 20 minutes. And feel free to ask questions, as I mentioned. This is your time, this is your benefit of being in this session. So the way I want to tackle and introduce deep learning here is going through logistic regression, because logistic regression is what most of us are trained on first, right? The interesting thing about sort of the history of deep learning is that there was little interaction between, on the one hand, the statisticians which discovered logistic regression, or who discovered logistic regression, and used it as a tool. And on the other hand, those computer scientists decades back who came up with the idea of a neuron and trying to... Hello, Gia, is there a question?
Hi, Chris. I'm sorry, there was a question from Muhammad.
Yeah.
For machine learning, if we are to, let's say, classify audio data using different filters to process the data, does the process data from each of these filters count as machine multimodal learning?
We'll get to that later. Very good question. The answer is it depends. It depends on whether you are covering something completely different, or whether it's just a filter that is sort of catches the same information. But it's a good question, but I think in roughly 2 hours you will probably understand the question better. Like you will be able to give the answer to your question to yourself. A very good question. Let's keep it in mind, okay?
Thank you. Sorry for the interruption.
Yeah, no worries. Keep them coming here, please. Yeah, but let's get back to the basics first and cover some basics. Logistic regression, okay? What happens in logistic regression? We have variables which are streaming in here, okay? And this can be features like in an audio stream. which are coming in different as variables in here, then we do something to this information, and we come out with, or we get a result, right? And in logistic regression, this result is 1 or a 0, and that's the prediction that we will get ultimately. So y hat, or in neural network terms, an A for activation for later layers. So let's take a look inside that neuron. What happens inside that neuron? Well, here in the neuron, we have first a linear component, which is the data that is streaming in here, okay, x1, x2, x3. And all of those x's will get a weight, right? And this weight in statistical terms is called the coefficient traditionally. And this weight sort of weighs the importance of this particular variable up or down, depending on how much it will contribute to our prediction later. Okay, then we add an intercept. We would call it from a statistics background, or a B for bias in the formulation of neural networks. And all this will give us sort of our linear component. And what we will then do is we will pipe it through a nonlinearity here. And this nonlinearity is in a logistic regression, a logistic function. But, you know, we've all heard of probit, which takes a normal distribution to model it, or any other kind of nonlinearity that have been developed about 15 years ago, like ReLUs, rectified linear units, or more fancy formulations of it. Anything does the job here, right? The point is that we want to have a linear component and then pipe it through some form of nonlinearity to get our activation, aka our prediction y hat. This is what happens in one neuron. And what deep learning does is it simply stacks those neurons. Okay, let's take a look at a shallow neural net first. So here we have still our 3 inputs, x1, x2, and x3. We have our final output neuron that's formulated in the way we just discussed. And then here for this example, we have 4 neurons that we plug in here, okay? And this gives us a number of different layers. So we have an input layer, which is the data. Then this is, in this case, fully connected to each of those neurons. So they will all flow in here, and here, and here, and here. Each of those neurons will give us an activation on the basis of how each of them was weighing the different data streams, right? How important is x1? How important is x2? How important is x3? And each of those neurons will have a different idea about how important those are. They will give their predictions to this final neuron. And this final neuron then takes these 4 results from that layer and weighs each of those neurons up or down, right? Like maybe this neuron is particularly good at predicting, but maybe that one is particularly bad, and it will adjust the weights of its own linear component. Or in more statistical terms, it will adapt the coefficients here accordingly, and then it will predict something in the very end, right? This is how neural networks work, fully connected neural networks. Now, how can we train these neural networks? And we're talking about training and not estimating them. That's very important. There is a mantra that you follow in the deep learning world. And this mantra is, first you predict something. It's sort of a forward pass of the information through your network. Then you calculate how wrong that prediction is. And then you propagate that information back through your network. And why do you propagate that information back? Well, you want to update the weights in your neural network. Okay? And you do that forward pass, calculate how wrong you are, backward pass, updating the weights, not once, but in many iterations, right? 100, 500, 1,000, 5,000 times. Excuse me, depending on how your network is. And this is how you predict, how you train this neural network. Okay, so you take the information, pipe it through these neural networks, and this neural, and through these neurons, and then that neuron. You calculate how the prediction is here, like the y hat versus the real y. You propagate that information back, and then you update the weights. Okay, this is how deep learning works in a nutshell. Now, a quick question to see whether you followed. Why would those neurons actually come up with different responses if they all see the same data? Right? That's typically a question I often get at this stage. Like, this is the same equation, this is the same equation, that and that, all see the same data. Why should these 4 neurons give a different answer to this final neuron here? And the answer is quite simple. You will have to select weights, the value of your weights in the beginning. Okay, remember that you multiply the data with a weight, aka the coefficient, and you need to do that already for your first pass. And if you initiated all those neurons here with the exact same weight, the whole thing would not work, right? And this is the reason why you need to initiate those values for the 4 weights actually at different values, at randomly chosen values. And this will determine how well or how badly your particular neuron is at predicting here for that final output layer neuron. So all this power comes from randomly initializing your weights here. If we build a shallow neural net, we can also build a deep neural net quite easily by simply adding more layers, right? Really intuitive, really straightforward. So we have our data here. We pass the information to those 4 neurons in our first layer. Okay, and each of those neurons will have a prediction, aka an activation for the second layer that is coming in here. Okay, this second layer takes the information from all 4 neurons here. Okay, and it itself will sort of weigh up or down how well or how badly those neurons are at predicting. And it will do its own calculation, come up with weights for it, and then give an activation out. And those guys here in the second layer do just the same thing. And we have finally a third layer, which does a very similar job and repeats the same exercise. And the deeper we get, the more abstract sort of information becomes, but there is power to be gained from both getting deeper, but also getting sort of wider in your neural network, and not just having 4 neurons in each layer, but more, like 32, 64, something like that, 128, 100, 200. The point is, irrespective of how deep your neural network is, we will always follow the same mantra to train the neural net, right? To calculate the weights here. And again, how does this go? Well, we first do a forward pass. We take the information and do the predictions on the basis of the existing weights and bias values, and see how wrong we are. Then here, if we compare our y hat versus the real y. We then propagate the information back through calculating gradients for each of the parameters that we want to update, right? We calculate the gradient for the weights and the biases in each single neuron, and then simply update the weights by how large the gradient is, right? Like if this difference here is very large, it might lead to a very large updating, and because the gradients are high. If this difference is quite small, then it might be smaller, right? If a neuron does particularly bad at predicting, then the individual gradient at this particular stage might be large, and vice versa. Okay, so this is how sort of fully connected deep neural networks work in a nutshell. And I wanted to refresh that so that we're all on the same page here. You might have run into deep neural networks, but you might have forgotten a bit how this works. On the basis of this, and this is now important for the rest of the day as well, people came up with different architectures, and that already back in the 80s and 90s, and sort of the second big wave of deep learning. And they had ideas about convolutional neural networks and recurrent neural networks. And these are really cool ideas. And what both of them do is that they allow us to model different data structures. So this data structure is sort of a classical regression framework kind of way of seeing things. And but there are different ways how data can look like. We're going to take a look at that now in a second. Okay. The one thing I wanted to show you first, and I almost forgot. So how can you think about deep learning, right? And that's a nice geographical interpretation. What we've seen here and with these neural networks is that we have neural networks which have a lot of parameters, right? Each of those neurons has a lot of parameters, a lot of weights and biases that need to be trained. Okay, and there are many more parameters than there are actually data points usually, right? And this is not a defined linear equation setting as we would have it in more classic linear optimization problems. We have a lot of undefined parameters, so we cannot estimate them, but actually have to train them. And the way, what we're trying to do is we're trying to establish this one really nice and neat decision boundary between one side of the data and the other side of the data, so that it can get to a 0 and a 1 in a very easy and cool and nice and clean way. And one geometric interpretation of this is that you can think of your data and the deep neural network as a sort of a decision boundary in a very high dimensional setting. And what we do with the weights and the biases is the weights sort of give direction of unwrapping and unfolding this high dimensionally enwrapped data kind of thing. And the biases will tell us how strongly we have to pull in order to get everything out. And if you do that in many, many different directions, and the neural network will sort of tell you how to do it, what you end up with is you sort of unfold your very high dimensional decision space into a flat line, and then you can easily decide what is on one side of it and what on the other. And the neural network basically does that sort of in a rough metaphor here. And I always found this is a really nice way of putting it. Yeah, Ivy, you have a question.
Ivy, can you turn on your mic? I think it might be accidental. So Ivy, if you have questions, you can also put it in the chat. There's also questions from Ubai in the chat on whether or not you can also repeat the working of the neural system, just to I think, help a little bit more with the understandings.
Let me see. A lot of stuff going on in the chat. The first one, yeah, I can do that. A second. So this one, very quickly, we get data in here. Okay, x1, x2, x3. This data is here. Every single one of those variables is multiplied with a vector of the with individual weights. So those weights taken together, they form a vector. You add a vector of biases. No, a single bias. Sorry, here you add a single bias, and this is your standard intercept plus coefficient setup, right? A beta 0 plus beta 1 x1 plus beta 2 x2 and so on. And this gives a linear component. This is a result z. And then you take that z and pipe it through a nonlinearity like a logistic function, for example, and this gives us your prediction. And that's basically how the neuron works. Okay. Have we covered everything, Hui? I think so. Okay, cool. Sumant has a question.
Hi, Chris. I just have a small question. In case of deep neural net, as we like add more and more layers, what about the impact on the gradient?
The impact of the gradient is it depends on the data, right? You never know, and you have to give it a try. And this is why there is no definite answer to these things about architectures. It's basically hyperparameters that you have to train. In deep neural networks, there is a lot of those hyperparameters, much more than in other machine learning models. And this is why you don't have one neural network as a model. Like neural networks are sort of a framework for coming up with all different kinds of models. And you simply have to try what works better and what doesn't.
Okay. And along with that, the activation functions, apart from the output final layer, the rest of the ones usually use the ReLU function, right?
Sorry, like what else? Like you are asking about different options for using nonlinearities?
Yeah.
Yeah, like the classic one was logistic regression, and what people did in the 80s. And then in the 90s, they moved on to the 10H function. And both of them are quite tricky for mathematical reasons. I would love to skip over here for that purpose and sort of reorient you back to one of the more foundational ones that are online. You can look it up deeper in there, but the main reason is you have a vanishing gradient problem, right? If a neuron is way out of line, it's really hard to get it back to behave nicely. And this is why people, and that was one of the reasons why out of a sudden around 2010, people could train deep neural networks. They came up with easier to calculate, more well-behaving nonlinearities like the ReLU function or the leaky ReLU or all kinds of variations of that. So over the last 10 or 15 years, ReLU have become the default, rectified linear units. The deeper reasons for that, as I mentioned, check it out in the videos and you can understand it there better, I think. But
Okay.
all the questions, right? Definitely.
Thank you so much.
Yeah. Cool. So this is really a refresher on neural networks. More details on that to understand it properly. Even within the DS3 framework, there's a lot of material already out there, and go and check it out. And of course, apart from DS3, there's the wider web where you can find answers to all these questions as well. But you guys, your questions are really good. Keep them coming, right? This is how we want it. This needs to be an interactive session. Okay, so this is deep learning, like fully connected deep learning, very basic. What we can now do is we can try to model different data structures. And we're going to take a look at sequences first. And sequences can be anything from the price of a share, right, in the stock market. It could also be a sentence. A sentence is a sequence of words, right? So any kind of sequence does the trick. And the first idea to sort of model sequences, and this is the most basic one, is a recurrent neural network. And what a recurrent neural network does is, well, we have data which sort of streams over time, right? We have multiple observations, a first word, a second word, a third word, or the price of a share on day 1, day 2, day 3. And they will have states, okay? And these states at time t will be determined at time t, of course, through the data at time t. But we also have information from the state of t-1, which is affecting the state at time t. And then this is with a forward pass ending up at our prediction yt. It's the result at t. Okay, this is a short way of writing this. Let's unwrap that a bit so that we can see a bit better how this sort of works. So remember that at t-, we had some input. And this input input determined the state at t-1 and a result at t-1. Okay, now we're at time t, and we inherit the result about the latent state here at t-1, right? This, and then we give that information to our latent state today and predict an outcome today. Okay, so it could be, is the company doing well? Was the company doing well yesterday? Might give us an information about whether it is still the case today in combination with the data that we're observing, of course. Right? Is this a happy sentence or not? You might have an idea about that after 2 or 3 words. And if I continue my sentence with word number 4, you might still have this idea given the value of the word number 4 and assign a state to that sentence, right? And this then gives sort of a final outcome. This is the most basic way of modeling sequences. There have been ideas for more complex models that sort of keep 2 different ways of this state. They're called, for example, long short-term memories, LSTMs, where you have a short-term memory state, which is stuff from yesterday, and you have a long-term memory state, which is stuff from, I don't know, a couple of months ago, that gives you a broader picture of what's going on. And these LSTMs, the ideas for that came out in the 90s already, but it took 20 years or so until the early 2010s until people really managed to train those neural networks, because the tools for training hadn't been around in the 90s and were only developed later. These are only some examples for sequences. And if you want to, the large language models that keep revolutionizing stuff at the moment, they're a fancy version of this, right? The large language models predicts the next word given the sequence of the past words. In the bottom, like at its core, these large language models can be sort of assigned to this sequence model family, in a sense, if you want to. So this is model for sequences, but now we also have models for sort of areas. And a typical way of modeling an area or a typical data example for an area is an image. Okay, so here we have this cute little robot. And what we will do is we will sort of come up with a way of having a predefined area that will analyze whether you find a certain geometric elements in that area here. And we're going to convolve with this sort of filter size, like with this 3x3 pixel matrix, through the whole image step by step, and as a sensor, and try to make sense of what we are seeing there. And we will have those convolutions that come out and assign them to feature maps. And these feature maps are specialized in detecting certain shapes, whether it's an angle or not, whether it's a line or not, whether it's a circle. And the higher we get in this, right, because we're going to repeat this convolution exercise, the more abstract these things become, and the more they are actually able to, those filters, to detect more complex structures. Okay, this is roughly how deep learning for computer vision works. In the very end, we will have a great number of filters that can detect all kinds of things. And we will have a fully connected layer, the stuff that we covered the first 10 minutes here, and that will generate us an output at the very end. Okay. The way the training works is as before. You take information, you do a forward pass, you calculate how wrong you are, you do a backward pass, you update all the weights. Okay. Training mantra remains just the same. There's also a nice DS3 session on computer vision, which goes deeper into this. So please feel free to check it out if you want to learn more here on this, about this. And once you are at this stage, you can start building all kinds of architectures. And this is why I personally love playing around with neural networks, because to me, it really feels like Lego bricks, right? You have a number of different bricks, you can do different stuff, and then you just plug them together and see how it behaves, right? And you can have easy one-to-one mappings where you have one data coming in and one output. You can have one data in and many different, like 2 or 3 different dependent variables, we would call them in social science. Like, is it happy? Is it a happy talk? Is it a talk about security policy, right? This kind of stuff. Oh, sorry. You can have many-to-one mappings where you have multiple data streams coming in and one target. You have many-to-many in a sequence setting, or many-to-many in sort of this kind of setting. Neural networks are hyper flexible, and in social science we've just started to work with them, and there's a lot that we can still discover with them, and that's why they are so cool, and this is why I'm all excited about the possibilities that we have these days. Okay, any more questions at this stage?
Nothing right now, Chris.
Right now? Cool, amazing. Then why don't we take a break here for 5 minutes and continue at 10:51 Berlin time. Yeah, do some stretching, and we'll see you back in 5 minutes. Hey, welcome everybody. Welcome back. Let me share my screen again. What did we do so far? We took a look at some foundations, and we wrapped our heads what it means, like how does deep learning work again, right? So we fully connected networks, forward pass, update, backward pass, update the weights. We had a look at models for sequences, recurrent neural nets. And we had a look at convolutional neural nets that help us to sort of take a look at data structures that look like an image, for example. It could also be, could use it for geography as well, right? Remote sensing is basically that. But all other sort of higher level geographic interdependencies, of course. So. Okay. Now let's jump right into multimodal learning workshop and do the next small chapter. This next small chapter is called multimodal data. So let's wrap our heads around what multimodal data actually is, right? Because we did a little bit of learning first. What is deep learning? Now we're going to take a look at the data and how the data is actually structured. Multimodal data, I think, has a lot of promise in social sciences, simply because it is the next level, I think, for us as social scientists to make full use of all the potential that lies in multimodal data. If you take a look at how social science has been tackling sort of unstructured data structures over the past 20 years, there is a clear there's a clear development in how that sort of behaved over time. We first went about 20 years ago from structured data, and by that I mean spreadsheet data, basically, as surveys, into unstructured data. And the first modality that we tackled, at least in political science, was text data. We came up with ways of analyzing text streams, and this really opened up a vast archive of text out that we could study quantitatively out of a sudden. Okay, if you think of a survey as something that you can do with a survey, is you can measure something at this moment in time. Okay, and if you want to travel back in time, you have to rely on other people, or I don't know, a former version of yourself who implemented a survey already if you want to study out political opinions or things like that. Now, with this structured to unstructured data move on text, we could analyze documents and speeches from way in the past. Okay, so we have a fully digitized corpus of 2 centuries of parliamentary debates in the UK Parliament. Okay, this is tremendous, right? Because we have a fully digitized version of data that is not how people remember how the past was, but really what people said 150 years ago in Parliament. And with the right models, we can analyze what people were thinking back then, right? This is a time machine that goes back into time. And this is already, to me, it's mind-blowing, these opportunities already and what you can make of that, right? And this has been a really rich data source over the last decades. People have been discovering that, well, maybe text's not all. And in the last years, you've seen stuff on audio data a bit more on image data. But still, we are stuck sort of with this one particular modality. Okay, this is how data sources developed in social sciences. On top of that, out of a sudden, we have a completely new data source, which is, for example, social media. And this social media stuff, take Twitter, now X, Facebook, Meta, Instagrams, like these were the first sort of social media channels. We then saw a wave of Instagram and Snapchat, which went away from just text to being explicitly focused on images. And now with, I don't know, TikTok, Instagram, YouTube Shorts, all these kind of platforms, you move away again from images to video snippets, right? So you see that the data forms that sort of go through society, that determine society, where society determines data, they've been evolving as well. And this bears great potential for social scientists to understand society. Okay, so data structures become more and more complex. The available data on society becomes more and more complex. And then at the same time, there's a lot of potential in that data because, yeah, just take a look at these two guys here, right? Barack Obama and Boris Johnson in the UK, who were heads of states from both of the countries. It's not only what they say is different, right? You will probably agree, if you've seen just one video of each, that both of those speakers are very different in the way they are speaking as well, right? And this can have really important information for us social scientists if we want to understand how politics works, how society works, to understand how different behaviors of those leaders sort of impact on society, not just through words, but also through the way in which these people are speaking. And this is why multimodal data is so cool to model, because there's a lot of potential in it. The thing is, multimodal data isn't really straightforward. It is a bit of a beast. And to understand that a bit more fully, we're going to take a look at something that's called the McGurk effect. I'll play that video in a second. If you can't hear it properly, try that at home later. You have the link at the slides. But there's something really cool that is happening here with this so-called McGurk effect. Okay.
Ba 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 ba.
Okay, this was the first audio snippet. Now take a look at the second one.
Ba 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 ba.
Second snippet, and now let's see the snippet number 3.
Ba 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 ba.
So what you probably have heard now is this guy doing 3 different audio streams, right? First he was saying ba ba, then he was saying the, and then finally he was saying va. Okay, this is what you've heard. The point is, and this is this McGurk effect, which is really powerful, the audio stream, guys, has been the same all the time. Okay, check it out and compare it by watching those 3 faces, which will be now in parallel, and each of them does each of those sounds. The audio is the same, but you will hear something different. Okay.
Ba 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 ba.
Okay, this is really, if you haven't been convinced of the relevance of multimodal data analysis, you should be now. Okay, and the very reason is we as humans can be easily tricked by different modalities, right? The sound modality isn't all, right? There may be more information that we sort of get in our eyes, and this will then merge to become a joint piece of information that we, even as humans, interpret in different kind of ways, depending on the relevance of the different modalities. Okay. We as humans experience modalities in different ways. Okay. We hear the modalities through language, words, syntax, speech acts, but we also hear acoustic signals. So this can be intonation, a very high voice or a very relaxed voice, right? Voice quality, different people speaking might affect on how you experience them. Vocal expressions, all that really matters. Then we have a visual component. The way I say something with my whole face or even my hands might tell you something different, depending on how my body language is or my facial expressions are. But we have modalities that go beyond that as well as humans. Okay, so touch is another modality. Smell could be another modality. But also any kind of body signal that we sort of emit, right? Our heartbeat is a modality that we can sort of use. And in the medical sciences, of course, MRIs or ECGs are used to sort of measure more data, more information on a human, right? That don't play so much of a role for us in our daily lives, but they are out there and they might matter. Okay, so this is data on humans that we can create easily and that are examples for multimodal signals. But we can also collect data about society in different modalities, right? A survey, for example, is one modality, one way of collecting data, because you distribute a piece of paper maybe, or do it in an online format. Governmental statistics might be yet another way of getting that data, right? It's another modality. Both of them could measure the same, right? Both of them could measure unemployment characteristics, something like that. The thing is, they come through different sources, right? There are different kinds of data. And then, of course, technology, right? Mobile phones, the internet, cookies, all the traces we leave online, the GPS module of your smartphone, or even your running watch, any kind of remote sensing that happens through satellites. These are all examples for multimodal signals, and we can all use them in social sciences to study society, right? This is so cool. And the point now is that these signals may be on the same thing, right? There may be different ways of measuring stuff, but we are measuring exactly the same thing. So how is unemployment developing? What's the perception of a party, of a governmental party? Is the president experienced as somebody who was a competent leader or not, right? All these different informations it's different information channels, but they might all describe the same thing, actually. This is where multimodality comes in. So let's go and define modality in sort of a computer sciencey, data sciencey kind of way, because this is where we want to end up in the end. So a modality refers to the way in which something happens or is experienced. So there may be different ways in which this something may be experienced or happening. But there is one thing in the end that we actually want to tackle. And there's a spectrum of closeness to senses that we can cover. Okay, think about the signal that gets to you. Okay, so in a way you might think about it as audio, image, or video data. Okay, so it's quite close to actually the sensor, like the raw material itself. But to really understand what's going on, you need to be able to sort of understand the language, right? If I would be speaking, I don't know, Portuguese maybe, or German, you might not be able to understand me at this moment, even though there is an audio signal, right? Nevertheless, my facial expressions, even though you don't understand the language, my facial expressions and my gestures might give you some ideas about what I'm saying, right? This might be one thing. And that's the next level, right? Basic object detection, language, and things like that. And then at a deeper, really level, you might experience more abstract things like sentiment intensity or object categories, things I'm talking about, all these things, right? So a modality, this information can come at different levels of abstraction, at different levels of closeness to senses, actually. Now, multimodality, and this is another definition here, is the joint experience of the same thing through several modalities. We talked about that already. There are different data streams that might come in, that might be combined, but this is multimodality, right? We can do this through several modalities at the same time. This stuff comes in a spectrum again, with regards to how homogeneous or heterogeneous these modalities are. For example, you might see the same thing through different cameras. Okay, This is what happens in some of the electric cars, that there is not only one sensor, but a combination of, for example, a radar sensor and a LiDAR sensor that is going on. It could also be texts in two different languages that are describing the exact same thing, but nevertheless, they are two different languages. It could be really conceptually quite different. For example, an image that you see, like a boy with a ball playing football, and there could be a description of that image, which is text, right? And it could say that there is a boy in this image that plays some football. And it could also be even more remote, like an image and socioeconomic data. Right? These are different ways in how you can combine these things. Let me just close the window because there is a construction site outside. Okay. So I think there was a question earlier about audio streams and filters, and I think this sort of relates to this. Okay, if there are two different microphones in a room, you would probably call it multimodal because it's two different microphones, two different sensors that are probably detecting something slightly different. But features from one sensor are probably more simply different features, different variables that are running into a classic unimodal model, and you're going to just process them through one stream of the architecture. That's sort of a first part of this answer to your question. And the second one, I think you can see it even more clearly when we take a look at code and how the architectures are really different between a unimodal analysis and a multimodal analysis. Okay, there are some challenges of multimodal data. Yeah, the literature mentions basically three challenges. The first of them is the heterogeneity of the data, stuff we just talked about, okay? So if you think about different data streams coming in, like a text, an audio, and a video stream, which modality helps you actually solve the task, okay? If you want to understand what somebody talks about, like the topic of a conversation, facial expressions might not help you that much, but you really need to take a look at the text or at the text and the words and to understand what people are talking about. If you're analyzing the sentiment, how happy or sad somebody is, yeah, the text tells you a little bit, but hey, the voice, the way how I am totally fascinated or just super sad about something, right? Or even my facial expressions really matter a lot if I want to understand the sentiment. It really depends, right? And this heterogeneity in these data streams really depends on the task that you want to do with it. It could be even the same data, but analyzing the content, one modality is like the text modality is important. With exactly the same data, the same video, when you want to analyze the sentiment, other modalities are more important. Okay, so this heterogeneity is important to bear in mind. Second piece of heterogeneity, think about the data layout, okay? And we will cover that in a second. But just compare the image, which is sort of a rectangle or something like that, to a sentence, which is a series of words, right? This is very heterogeneous. How do you get those two data things together, like really in the mathematical sense, because you want to model them in the very end. And then if you think about the data representation at this stage, and there are different atomic units in those data structures, right? Language consists of individual words with maybe even a hierarchical structure on top of them. And audio data are waves, right? That you have to sort of at different frequencies cut through. And images are made up of pixels in different, intensities on the RGB scale, for example. So this is really challenging to get together, right? How do you get an audio wave and pixels together? Challenging to model. The second challenge is connectedness. Okay, so a correlation of signals might be really straightforward, right? You saw my hands clapping and you heard the voice in here, the sound in here. And this is straightforward to model, but the connectedness might be really quite semantic rather, right? So a wink and saying something is connect it to some kind of sarcasm, for example, that you could do, or a joking behavior. But it's really hard to model this, right? Like this clap is really easy to detect in the data, but you need to have a very deep semantic understanding of what's going on in your model, not as only as a human, to understand deeper signals. And then all these modalities that are coming in, and for now, here we focus on text, video, and audio, they might interact in different ways. And this is a really cool table, I think, to illustrate that. So you can have separate components or multimodal composite signals where you combine them. And you can have redundancy and you can have non-redundancy. And you can go through and think through each of those four quadrants here. Let's focus on this one for now because it combines non-redundancy with multimodal composite signals. So we have the modalities A and B, and they can get to two completely different predictions, right? And two different things. It might be that the modality A is dominant. So in the end, for what you want to do is you're only concerned with the square here, right? Think about this. So when you analyze the content of a video, audio and video itself might not be important, but the words might really matter. So the words will really dominate all the other modalities here. It could be that B is modulating what is happening in A, right? It could be that my facial expression is really modulating the sentiment of of the text and the audio stream. It could also diminish it, of course, right? And finally, A plus B might lead to something completely different that you can only discover if you join those two modalities, and that would be then called emergence. So you can have all kinds of these cross-modal interactions that are going on there. And this really makes this multimodal data analysis challenging. Okay, so we have great opportunities in modeling multimodal data, but this modeling is quite challenging, actually. And doing that in a clever way will help us unearth a lot of potential that is in this multimodal data, but you really have to carefully think about what you're doing if you want to get the most out of that data. Let us take a look at 3 examples from current political science literature, stuff that is out or in working paper format. And we will get back to them at a later stage again. But let's go and take a look at what some other people are doing. So there is a working paper from Ollie Ridman and some colleagues who take a look at legislators and whether they are like to deliver emphatic speeches if district preferences align with their vote choice or not. And what they do is they take a look at the video and the audio input, and then they predict speech emphasis on the basis of 2 second segments. Right? This is one paper. Then there is a paper from Bryce Dietrich and colleagues who take a look at responses in a video setting as survey responses, and they use video, audio, and text to identify the emotional intensity associated with the responses. And this is not only in an in-person setting, but online and a telephone setting. And finally, Dietrich and co-piece that is out there already that takes a look at COVID-19 coverage, and it sort of mixes image data and text transcripts and checks whether Fauci, who was sort of one of the main medical figures during the pandemic in the US, is present in news coverage, and whether his presence changes the content of the news coverage. Okay, this is, and then these are some examples of what people are already doing with multimodal data, and we're going to revisit those examples later. But that's already a first serve on that. Do we have any questions at this stage, Hui? I don't think so. Rima asked whether we can say that neural networks are connected with relevant hashtags we use. Depends on the way how you model it, of course, right? You can just model hashtags if you want to, but you can also model, yeah, you can model the complete text. That really depends. I hope that answers your question. Somebody asks the modal part. So a modality is one way of seeing the data. Okay. See whether I can get that a bit larger. The definition of it is a modality refers to the way in which something happens or is experienced. Right. Think of one sensor that detects reality. I think that roughly summarizes it. Okay. Any other question? So Rima asks if there is a picture of a sun, and will there be a hashtag connected with the sun? I don't understand the focus on hashtag of it, to be honest. If you use the correct model, the correct multimodal data, you will see a picture of a sun and then see the word, this is a sun, or the sentence, this is a sun, for example. So you don't need to have the hashtag here, but you can, of course, have a description. If you build in your model that you just want to focus on hashtags, like in a social media context, of course, you could probably model that as well, right? So hashtag is just one way of expressing words. I think this is what I want to say here, right? You don't have to narrow this down on hashtags. Okay, let's crack on. And keep your questions coming. They're really good, right? So what did we do just now? Well, we understood what multimodal data is. We understood what the promises in there are, what a modality is, what multimodal means, and what the challenge multimodal data are. And we also had a look at some examples in political science that actually take a look at multimodal data. So let's cover the last bit of the foundations before we take another break. And this is about representation. Okay, so how is multimodal data represented? Remember that we talked about how challenging it is to get this heterogeneity together, like how different a sound wave looks from an image data, for example, or a socioeconomic survey or something. If you think about the numbers behind it and how they're structured, completely different. So how on earth can we get them together? And one development that happened over the last 10 years, maybe, really helps us. Okay, and the secret in this that people have been playing around a lot is adding representations. And this is what we will tackle now in the next one. Let's start with language. So, the classic way how we can represent language data is something called term document matrix. Okay, so here you have this basically a matrix where you have the vocabulary here. So each row is one word in your whole vocabulary. And then each column is a document. And you simply count how many documents you have, how many of each of the words you have in each document. This is a way of representing your whole corpus, right? This is how it's been done classically. And like the first versions of search engines basically built on this idea, and it is pretty powerful. It gets you already very far, right? In political science, the first models have been built around this, and you can estimate fairly well how left or right somebody is when they talk on the basis of this, or what they're talking about, right? All topic models, think of latent Dirichlet models, work on that basis. And even it works even though you lose the structure of the sentence, right? Because a document, how will it look, right? It will be one column here in your term document matrix. But it's still enough information. That's pretty cool and powerful. One thing you also notice is it's quite static, right? Imagine you have 10 documents, and now you have a document number 11 coming into the corpus, and out of a sudden you have new words that appear only in this document. So what do you do to the whole term document matrix? Well, you need to add some more lines that will be all 0 for document 10, but only have a couple of entries for document number 11. So it is static, okay? It is not a dynamic thing. It's quite challenging if you want to work with sort of a data stream that is coming on a live basis, like a Twitter stream, for example, where new hashtags, new abbreviations, and new things might pop up all the time, right? So people came up with a new idea, okay? And this was about, like, it was realized about 10 years ago now. And it is built on the idea of, well, maybe in order to understand language, we don't need to model grammar and structure of sentences, but maybe the context is enough for us, right? So this distribution hypothesis basically states that the meaning of a word can be approximated by surrounding words. And I have this great example that I took from a lecture from J.P. Morenzi, which is all about the meaning of bardy walk, right? What does bardy walk mean? And I'm pretty sure the vast majority of you guys, please don't Google it, have no clue what bardy walk actually means, okay? So we're gonna experience now this distributional hypothesis and see what bardy walk actually means, okay? So here's an example sentence. He handed her a glass of bardy walk. It looks like a beverage, right? Bardy walk maybe is something you can actually drink. This is really nice. This is really cool. And let's have another sentence. So we infer that information simply on the basis of the fact that apparently barley wort is something that you have in glasses, right? But it could also be, I don't know, a jar, right? With fruit in it. We still don't know it yet. Let's go and see the next word, the next sentence. Beef dishes are made up to complement the barley works. Okay, so we know it's something to eat or drink. It goes well with beef. That's an information, right? So it probably is not a dessert that we're talking about here, something sweet. Nigel staggered to his feet, face flushed from too much barley work. Oh, wow. This could be alcoholic, right? Barley work, actually. And then Malbec, one of the lesser known barley work grapes, responds well to Australia's sunshine. Oh, I see. I guess I see where we're going here, right? Barley work could be some kind of grape, and maybe barley work is some kind of wine. I dined off bread and cheese and this excellent barley work. Sorry for the typo. The drinks were delicious, blood red barley work as well as light red sweet Rhenish. Okay, so it's a red wine apparently. And this is basically the distributional hypothesis in working, right? So about a minute ago, you guys had no clue what barley work is, and I didn't explain to you what it is, right? But you inferred its meaning on the basis of a couple of examples. And this is what embeddings are at the bottom of the heart, right? So what word embeddings are, they are a clever way of reducing this large term document matrix into something that's much smaller. Okay, so for each term in a document that exists in the corpus, you will get a 2, 3, 500 dimensional vector like a vector of length 500, for example, that sort of represents its meanings. And the first models around were the Word2Vec and Glovey models, but also other stuff like Bert, Roberta, and all kinds of variations have come out here that help us understand what words actually mean at the bottom of the heart. And the beauty of them is that, in particular for large corpora, right? Think about a corpus of hundreds of millions of tweets, right? This is quite a big matrix if you want to do some analysis with them. but we can now represent something trained using those data in a much shorter matrix, which is the words times 500 basically. This is super powerful. So I don't know, a 5,000 or a 10,000 by 200 matrix. That's quite handleable for computers. And you can then do things with word embeddings. And this is back from 2015, a nice example. You can, if you have a degree of closeness in a high dimensional space, you can compare document 1, Obama speaks to the media in Illinois, to the president greets the press in Chicago. And you can see that the words themselves are very different, right? If you just use the term document matrix, these two sentences would be completely different. But in the right context, of course. If you have a representation of the meaning of the words from back in those days, you can see that Obama is close to president, speaks and greets is similar, Illinois and Chicago is close, and press and media is close. So you can align them fairly easily and see actually that those two sentences are quite similar. Now, if you do embeddings with the words, you can also do them with images. Remember, when we covered convolutional neural networks, we have this feature extraction stage that goes through layers of convolutions and filters. We then in a classic convolutional neural network then have the prediction stage down here. But what you could do is you could simply pipe one image through here, through this feature extraction phase, and get a 64 length vector out here. And this is basically an embedding representation of your one particular image, right? This is a feature representation of one image that you can build from that on the basis of a trained neural network. So what it allows us to do is we can not only represent words with embeddings, but also images with embeddings, right? And that's very powerful because out of a sudden, we can see a bridge that we might want to cross where we get across the idea of, well, this image data structure looks so much different from my text data structure. How on earth can we map them? Well, now we have two kinds of embeddings that we might want to add and then combine in a clever way. This is a bridge towards that, okay? And yeah, just a quick reminder that this is how those filters in those convolutional neural networks may look like, and these are features that we can get out of them. The big point that I wanted to make here at this stage is that we can use embeddings to get from one modality, a text modality, which looks very different in sort of how the data looks, and an image modality, and also the same also for an audio modality, which I'm skipping here, to representations, right? The representations of what they actually mean. Let me see whether we have some questions here. So I haven't seen any questions so far. If there are no questions left, let's take another 5 minutes break here, okay? So meet you back at 35. And the next stage, we will then take a look at some basics already. Cool, so see you in 5 minutes. Still muted, even after 3 years of pandemic. Okay, so welcome back, everybody. What have we covered in the last sprint? Well, we talked about what multimodal data actually is, and how challenging it is to get things together, maybe. And we already learned about a clever way that points us a way to, well, how we might get around a couple of those corners, right? And that is different way in how we can represent the data, okay, the data stream that is coming in. So remember that like a camera as sensor detects pixels, which come in a square format, and a text transcript might be a series of words. But if we use embeddings, which is a vector length 100, 200, 500, it might help us. It might help us understand how things go and what is it, right? And clever ways of representing them can be of representing an object, be it through text or image or audio, whatever. If we get those representations out, we might be able to, stick them together in one way or the other, right? And this is pretty much where we will be going here with that. This is what has been developed over the last, I don't know, 6, 7 years or so, 8 years. Let's cover multimodal learning and a clever way in how we can fuse those modalities. And let me share you my screen here again so that we can get started. So, we talked about the fact that we can have those representations of different modalities as embeddings, and why not fuse or bake them together in one way or the other, okay? So what is a multimodal fusion? Well, it's a process of joining information for modalities, from different modalities for prediction, right? In the end, we know that those modalities cover the same stuff. So if we have good representations of that data, it should be able to, describe what we're doing. Some examples, think about audio-visual speech recognition that might be going on here. Audio-visual emotion recognition. Is this person upset? And given what we're seeing in this video, speaker identification. Who is it that is talking, right? We have a face, we might have an audio wave that is coming in. Who is it actually? And so on. Very many different ways and how we can fuse that information in a useful kind of way. So let's cover some basics in ways in which we can fuse everything. Let's take a look at some building blocks here. Okay, so we might have features or decisions that are coming in here, and then we have an analysis unit, an AU, and that comes up with the decision. Very straightforward. Okay, so we have data coming in, an analysis unit, and it comes up with a decision. We could also have a feature fusion unit. Okay, so this feature fusion unit has features or variables coming in, and it basically stacks them into something different, right? It's this having an image maybe coming in and popping out and embedding, for example, right? There's no decision involved. It's simply rejuggling the data a little bit and coming up with a feature fusion unit. There might also be a decision fusion unit, right? It's decisions coming in, and those decisions are sort of fused and baked together in one way or the other. And these are already three core building blocks that we need. And something that we can do with them is something called early fusion of that information. Okay, so we have fusions that are coming in, feature 1, 2, and so on. We're going to pipe them through a feature fusion unit, and however this looks like. Then we have an analysis unit that takes a decision, and we have a decision in the end. One way of thinking about this feature fusion is basically concatenating, right? So just sticking them on top of each other might already be feature fusion, or it is feature fusion here. We use the correlations between those features to come up with a result in the analysis unit. There is one learning phase here in this analysis unit, of course. The problem might be high dimensional, but the analysis unit ideally doesn't care. You can run into problems here if you have different granularities between modalities. Okay, think about a text that comes in, and at the same time you have video data. Okay, so video data, you have, I don't know, at 40 hertz, you have 40 images per second that are coming in. So how are you going to match that information to your word, right? An easy way out could be to chop up the video stream according to the words, and then just take one image from the time it takes to say one word and just use that. But this is a workaround, right? We need to come up with good ways in how to do that. Quick recap: what do we have in terms of like what are the Lego bricks, so to speak, that we have for building neural networks and that we could use for fusion? And remember that we have different features that we can work with: variables, text, video, audio, embeddings, images, all the different stuff here. We have different kind of models. We have the fully connected networks. We have the convolutional neural networks, the recurrent neural networks. This is stuff that is out there, and then we can connect them simply by sticking them together mathematically. And this is how early fusion with neural networks could look like, actually, right? We could have text coming in and pipe that through a recurrent neural network. We could have images coming in and pipe them through a convolutional neural network. We get embeddings out, right? We simply concatenate them, stick them together on top of each other, and then have a deep neural network decide what of those information pieces it actually wants, right? So it could be a 100 long text embedding and a 50 long image embedding. We're going to stick them together to a vector of length 150, pipe it in the deep neural network, and let the deep neural network decide what it wants to use for prediction, right? Pretty simple, pretty straightforward. We could use variables like socioeconomic variables and have a fully connected layer here and image here, pipe it through a CNN, stick them together and have a deep neural network here. And this could help us predict, right? And this is one of the examples that we're going to take a look at later, actually. Instead of just two modalities coming in, we can have three, right? A video, okay? We can have video that is piped through a CNN, audio, you can pipe that through a CNN if you want to, a text embedding through a recurrent neural net, stacking it all up, have a deep neural network, checking the embeddings and learning from them, and then predicting a target. Really straightforward to do early fusion with deep neural networks. Think about how the data should look like, right? raw data, of course, doesn't properly work. So you really want to convert them into embeddings here, because then it's much easier to process. This is simply to really hammer out that, of course, it doesn't look like that. You ideally have those embeddings, and this is why these embeddings are so cool. So if there's early fusion, there is also late fusion, of course, right? How would late fusion look like? Well, late fusion means that you have a number of analysis units that come up each with their own decision, right? Is this a happy speech? And you have your model, a first model that just takes the texts and comes up with a yes or no. You have a second model that comes up with a yes or no on the basis of the image data, and you have a final model that takes a look at the audio data and comes up with a yes or no. And then you combine those three decisions with yet another analysis unit, and this gives you your final decision. A point is you need probably multiple training stages because you want to train those guys here before. Then there are different fusion mechanisms here actually in place. You could have a voting, you could have weighted sums or whatever. Again, granularity of the features might something to think about. The cool thing here is it's less of a problem because you only have to aggregate those decisions, right? So that's simply something that you can model well with it. However, the level of interactions between the information that comes in here is actually quite limited, right? Because you only take a look at the decisions, but not at individual points in your data streams that are coming in. So the question is this ensemble learning or not? Right? A very interesting point. Something to bear in mind. The point is, it's not quite ensemble learning, right? Because in ensemble learning, you would have the same data coming in with different analysis units. But here in multimodal learning, you have different data streams that look different, which describe the same stuff, right? So it is sort of some kind of ensemble learning, but not 100% of the classical ensemble learning that you know from, I don't know, a classic machine learning approach where you have a couple of models using the same data and then you weight their decision in some kind of way. Late fusion with deep neural networks, again, really straightforward, right? You have images with a CNN, they take a decision. You have text that uses a dictionary and you have a decision. And then you aggregate those decisions with, I don't know, a fully connected player or maybe even a support vector machine or, I don't know, a random forest, whatever you prefer. And you can aggregate them up to a decision. Is there some kind of question? Nope, I think that was just some audio coming in. Okay, cool. So if there was early fusion and late fusion, we can also have hybrid fusion, right? Which is a mix between those two, right? You might have a analysis unit in here. This is just for collecting features. This gets soaked up into feature collecting thing, and then you have a final analysis unit. It can have the advantages of early and late fusion. For example, you might have this opportunity of interacting at lower and higher levels, but the training and the complexity of the model can be quite high. Now, the cool thing is with neural networks, you have the opportunity to really model hybrid ways of doing things in a really cool and clever way. So, for example, imagine you have a convolutional net here that is pre-trained. Of course, you can take the embeddings that come out of piping your image through this convolutional neural network here and have, I don't know, maybe a second modality, an audio feature that comes through here, and you take the embedding here, and then have a sigmoid that analyzes everything, right? But, and that's the really cool thing about that, that's a thought that you need to have, right? Like, why do you only have to take out your embedding from the last layer of the convolutional neural net? Why not earlier, right? Why not just right after the first layer as well? Because, hey, there might be some different kind of information that isn't there. And you could pipe that already here through a rectified linear unit to get some decision. And the same for your audio model, right? It could be that you just take the last layer, but you can take a different layer as well. Nothing stops you from that, right? But once you open your mind to this possibility that you can take features from different levels, you're like, wait, like, so which one do I take, right? It could be any of those layers actually. This is what this pretty cool paper does. It says, well, why not take them all, right? Let's have two basically convolutional architectures, for example, here. And we're just going to take the embedding of data that streams through here at each single stage, right? And the same for the other modality. And we're going to all pipe them into one analysis unit, for example, a deep neural network here, and let it decide which of those is the best thing, right? Like, what of those embedding layers is best. And if you write your cost function for your deep neural network, you can simply have the cost function at those three different layers, add it all up to a general cost function, and train your neural network in that kind of way. Really cool way of doing hybrid, yes, some hybrid model architecture, hybrid fusion here, right? And it is all possible because we are going away from a world where we only have an image as an image representation and an audio stream as an audio stream representation, as some kind of wave, but where we sort of pipe them through some maybe pre-trained model in order to get some kind of higher semantic representation of what's going on. And then we can take those semantic representations that we can't interpret as humans, but simply give it to a neural network and see whether it works well or not, right? Check out that paper. It's really cool and quite yeah, mind-bending in that sense of opening up yourself to this opportunity that you might want to get information from different layers in a neural network. So there's a first stop here where we take a look at some code finally. Let us take a building code with Keras. We're gonna, like, I chose Keras because it's sort of for beginners the easiest framework, right? And there are others. Torch is typically the one most scientists work in because it's a bit more flexible, more open. People have moved a bit more there. There are yet others, and these are basically high-level APIs that help us express neural networks in an elegant kind of way. Let's go and take a look at the code number one and at Google Colab. And I prepared something for you guys. I can't see it, but I don't think there were any questions in the chat. Oh, there are two maybe.
There is questions on how to combine different decisions units.
Yeah, so you can combine them with whatever model you want, right? Think of the outcomes of decision units as features for another one, right? So it could be 5 decision units. One says this is happy, the other one says this is sad, the other one says this is happy. A very easy way of aggregating it is a majority vote, like you would do it in ensemble learning. But you can, of course, use a fully connected deep neural net if you want to, if it is a bit more complex. You can have other machine learning models like a support vector machine or a random forest, or even a logit, whatever. You can combine them in all different kind of ways. It really depends on the task that you want to do, okay? Cool. So very quickly, this is the GitHub page, and you can find the link here for Google Colab for the code number one. We already posted the link to Google Colab for you guys here. you should be able to access it, and you can play around with it on your own. You can't break anything, right? It's not like Dropbox or a joint document. Everybody will live in their own world. But it's really handy for me to show you what's going on here. And if we had more time, we'd have an interactive session, but I'm seeing there are like more than 80 people here in this chat room, and I can't go and visit you all to see how things are working. There are even more people outside on YouTube. So what I'll do instead here is, for the sake of this particular workshop, I'll just walk you through the code to show you how easy it is. And then I commented it really well, so you should be able to work through it on your own later on. Get in touch afterwards, right? If you run into problems, I'm really happy to help you guys out. But it should be all pretty self-explanatory. So all we do here is we use Keras for model fusion, and let me take it away for you. So some housekeeping. We load TensorFlow. And TensorFlow is basically this Google written API for modeling neural networks, and then Keras is yet one level higher, and it sort of writes TensorFlow below it. And if you've studied convolutional neural networks, for example, the stuff that's online with DS3, you might have seen this sequential way of writing a neural regression model. And the way this works is you, oh, I shouldn't do that. I'll need to execute those two lines again. So the way this works is you define your model, and then you simply add layers, right? And you add a dense layer that has 64 neurons. In the first layer, you have to define the input shape that here for the sake is 10, for example, and then you provide it with an activation function, your nonlinearity basically, and it could be a ReLU. Then you add a second layer with 32 neurons and have another activation function that could be a ReLU here. And then you have a final activation layer. Okay. I have a question here whether it's possible to annotate the notebook. I hope this works well for you guys, right? It's fairly introductory, and as you see, there is a lot of stuff going on that's pretty easy. And I thought it's pretty self-explanatory because this is stuff that I'm assuming you guys know already. It's simply a reminder for you guys to check it out, to check out the previous videos that are online already that can help you with if you really want to dig deeper into that code. And you can always go back and listen to the recording. I'm going to explain it to you now. Okay, so I hope by following here you will be able to understand this. But of course, feel free to ask questions in case there's stuff that you sort of seem to miss a bit. And as Hui already points out, feel free to tag along, right, and annotate through our explanation here. The point here is this is a classical way of writing up your model. Now, if we want to build multimodal data, we have to rely not only on the sequential framework, but we want to take a look at the functional neural regression model. Like the way Keras is working is slightly different. So the first thing you want to define are the inputs, okay? And for this example, we have basically a data format that has 10 columns, so 10 variables, for example, that you might have. And then we have a first model, and the first model is having 64 of those neurons. You have an activation function and the input through, and you add it to this object X, and then you add another layer with 32 neurons and a relu activation function with X. And then you have a final layer that comes out of it. You then turn it into a proper model by calling keras.model, and you have to define the inputs here. And this is sort of the model architecture. And if you then take a look at how the model looks like, you again get back this really, it's the same model as above, you were just writing it just slightly differently, right? So it's pretty self-explanatory, actually. You can see the parameters that are being made, the output shape, right? And this none really depends on sort of how many data observations you send through each time on your batch size later. But this is how you write one branch of the model, okay? Now, we want to do model fusion. So we don't only want to have one branch of data that is coming in, but we also want to have a second branch of data that is coming in. So let's go and define it, okay? So we will have two different inputs that are coming in. We will have an input A. It could be an embedding, for example, that comes out of an audio stream or an image stream. And we will have input B, which is, for example, embedding for text. So let's call them input A and input B with different shapes. Okay. Let's take a look at the first branch on how it operates on the first input. So we have input A that is being piped into a dense layer with 8 sigmoids. And this layer then adds into one that has 4 sigmoids. And then we want to build a first model. Okay. And the first model is the inputs are input A, and we will call the outputs X. Now, the second branch that operates on your second data will come in as input B. Since there's a bit more juice in the data, right? It's a bit larger. Let's define 64 sigmoid units here, then 32 and 4. And then we're going to stack them together again by defining the inputs, the outputs, and keras model that are going on here. Of course, the exact architecture here it's completely arbitrary, right? It's simply showing you the basics and how easy it is to get such a toy fusion model together. Okay, so what we will do now is to get the first branch and the second branch, and we're going to combine those two outputs. So with the function layers concatenate, we're simply going to concatenate the outputs from the X model, this one here, and the outputs from the Y model, this one here, and simply stack them on top of each other like this, these two embeddings, right? This is what we're doing here. Now that we have those two embeddings that are concatenated on top of each other, we will define after that a final decision unit that we will model with a shallow neural net that has first 2 sigmoids and then a final decision unit here, and fully connected layer by giving it the combined object. And this is the combined object here, right? Remember, it's this fusion. And build this model and then turn it into a proper model here by defining the inputs from the first place, which is input A and input B, input Y and input X, sorry. Then we will call the output Z. This is the model fusion. Okay, so if we call the summary function on model fusion, we get a nice summary of what's going on here. Okay, so we get the input layers, which are here. We have the first branch that is coming in, the first layer, and it's the 64 and the 8. And then we have the second branch coming in, and we're going to concatenate everything and get the final output. And this is the nice summary of it. Okay. Really straightforward. And simply a toy model that helps you in how to build this, helps you learn how to build this this structure. And if you want to know more about it, like even more information about it, there's stuff on Keras that you can of course follow. this is also a nice first taster of how this goes. But this code, this first code that we cover, is really showing you how easy it is to use the functional API of Keras to build everything. Okay. Are there any questions at this stage? This kind of code about things that are going on here. We do have time for any kind of question you might have had about this morning. Okay, I can't see any question. Let's quickly go back and use the 10 minutes to see what we've been working with, to understand what was going on. So what I showed now, right, the code that I showed you guys now is an early fusion model, right? You've seen that. So you could think of it as code for an architecture like this. Okay, so we have some text. You might have piped. Yeah, well, here we have two convolutional neural nets, right? In this particular example, we are piping this data through this one convolutional net, and here another convolutional neural net. And then we have a fully connected layer that gives us a decision in the end, and then this is sort of the accompanying architecture for it. Cool, so you understand how to do fusion already, and then how to do that in a very easy way. Let's go back to these political science examples that we visited quickly in the first place when we talked about how multimodal data looks like, and see what those people have actually done. So Ritman, Ringwald, and Nijhuis, what they do is in their paper, they have two data streams that are coming in. Okay, they have a video input on what's going on in Congress. They have an audio input, and then they, in both cases, use a pre-trained convolutional-based network to come up with embeddings. Okay. They simply concatenate those embeddings and have a fully connected layer in the end. And then they calculate a speech emphasis that goes from +3 to -3. Okay. So they synchronize this video input on the basis of 2-second segments, do this diffusion network here. The fusion mechanism is simply concatenate those features on top of each other. And then they train this with a low learning rate, right? An Adam with function with low learning rate. So knowing what you can do these pretty cool papers already now, right? This is really powerful. Let's go and take a look at the next example. This is the Dietrich, Mondak, and Williams working paper that's circulating at the moment. So what do they do? And I'm taking again the figure from themselves. Is they have an audio convolutional neural network, an image convolutional neural network, and a text recurrent neural network. Okay, and they fuse them here again with early fusion. So they come up with embeddings that they then concatenate, and then they train the whole model altogether. Right, really straightforward. Again, an example of early fusion, and you know how to build that already. Now, the Finding Fauci paper that is out already, it works a little bit different. So here they take a thumbnail image of a report from the Internet Archive, I think. Then they do some celebrity recognition with a proprietary model from Microsoft, the Microsoft Azure API, and they want to detect whether Fauci is in it or not. And then they take the text from the thumbnail, pipe it through a dictionary, and identify the health and death mentions. And then they do a negative binomial regression to understand how things are working here. This is an example of a late fusion model here. Okay. The lower level models use proprietary AI here. And dictionaries. And the high level model here is a negative binomial, right? Somebody asked how to combine that in a way. A negative binomial might simply be one even though it's classical econometrics, one way of doing it. And the fusion mechanism is at the decision level. And the synchronization or the alignment here happens at 1 minute segments that they simply take. There's another question here. After giving such a huge heterogeneous data to the decider, what is the processing and time requirement to replicate this work? It really depends on what you want to do with it, right? And how large your data is. The toy model that I showed you guys is fairly easy to handle since it's a small neural network. We're going to take it a real example after the break. And again, it really depends on how complex your data is. If you build a small model with a couple of layers only, this is quite handleable, and you could even train it on your own computer, maybe. If you have a bigger machine available with GPUs or other architectures of processing units, this stuff can be parallelized fairly well. You might be able to still work with your desktop machines, but if it is more complex and more encompassing, you have to outsource it to maybe the cloud, which is a larger computer standing somewhere else on this planet. This is simply quite computation intensive. So if you don't have access to a GPU, it really depends on what you want to do, right? Neural networks are quite heavy when it comes to computing resources, right? There is no surprise that big GPU building companies are currently the star of the stock market because all this stuff is trained on GPUs. As you will see, the stuff that we do in the afternoon, this is stuff that you can really do on your own computer. And I think for sort of the smaller scale social sciencey kind of stuff, that might already be enough. But if you really want to dig deeper and come up with deeper analysis, then having access to some GPU might really help you quite a bit. If you don't have, if stuff is really complex and you notice that your computer breaks all the time or that it's busy all the time, there is scalable computing power on cloud services, and there are many different out there that work pretty well. If you're in academia and if you're a student, for example, there might be there are programs out there where you can write them an email, say, hey, I'm a student in that area. For this project, I would need a bit more computing time, and typically they're quite responsive. So yeah, there are ways around that. And typically, at least, and I know this is a Northern Hemisphere privilege, universities or groups of universities often have compute resources that you can join. If you talk to your IT guys at uni, they might help you come up with solutions for that. That's typically something that is available out there. I know of colleagues who work in I work quite a bit in South America in my life, and with colleagues there. And even though they aren't as privileged as Northern Hemisphere universities are, typically people do have access to something like a basic GPU or something. You don't need anything super crazy, right? But it should help you sort of do the first steps in that area. But my recommendation, if you're new to this area, just give it a go and give it a try and see how far your own computer gets you. And if you notice that stuff doesn't really work out, then take the next step. Don't start with GPUs right away. I don't think this is, it's worth a time investment. It requires a bit of an overhead sometimes. Yeah, give it a go with your own computer first. And in particular with modern architectures, if you have a recent machine, it should already get you quite far, right? And that's, I think, my recommendation. So if you want to do real complex stuff, like further down the line, and you're a bit more of an expert, GPUs actually do have a benefit in there, I think. Yeah, okay. So I can't see any other questions at the moment. Let's break here for 15 minutes, guys, and come back. and see let's wrap our heads then about some more of the more complex things. Okay. See you in 15 minutes at 12:30 Berlin time.
Anywhere you go, you belong. Anywhere you say, anywhere.
Hey everyone, I hope you made it back safely. Yeah, welcome back to the session. We took a little longer and anticipated some stuff the afternoon because I really wanted to to show you how the code that we've been covering actually works in political science realm and how those people are tackling it. So what did we cover in sort of the first half of this workshop? Well, the first half of the workshop was basically a refresher in how deep learning actually works. So I could really scratch the surface. There's plenty of material out there. If you need more information, feel free to get in touch with me. Then we went on to talk about multimodal data actually. What the key challenges of multimodal data are, and how we can make use of those clever representations, these embedding representations, to represent all different kinds of data structures into a fairly similar format, aka a vector of length, I don't know, 100, 200, 500. And then how we can stick those vectors together to build easy forms of fusion networks that help us do multimodal learning already. Okay, and we had a look at a toy example, how to do that in terms of code. We also took a look at some examples from political science that are currently floating around, how those people do it. And yeah, let's continue on the ride and go right back to the code to see how you can build a real working model for you. Okay. So let me share my screen with you. Please keep your awesome questions coming, right? They are really good. This is really cool. I really enjoy this. So I have my window in a way that I can hopefully see whatever is going on in terms of chats. Keep your questions coming, okay?
There was a request to increase the screen size, if it's possible.
Increase the screen size. Better.
Perfect. Thank you so much.
Yeah. Let me close the window behind you guys because it's a bit confusing. Cool. Yeah, let's go. Predicting house prices. So some housekeeping first. Load a couple of modules, right? This is not really interesting. What are we actually doing? So this really, it's yet again another toy example. Okay, it is supposed to show you how this stuff is working in an easy way, so that you can wrap your head around it. It is also data and code that you can you can download the data easily on your own. All the links are in the module, are in the workbook here. And the problem is also a problem that is safe to run on your own computer if you want to run it locally. Or here we use Google Colab. It's like Google Colab is a cloud service. All the calculations that you run in your browser don't run on your own computer. They actually run on one of Google's cloud solutions. And typically, if you don't pay for them, you get like a default thing. And then for teaching, it's yeah, but it's one way of doing things. And yeah, of course, right? If you want to follow this on your own, go to the Google, go to the GitHub page from the module. Code number 2 is the link, or we also just pasted it online. So thanks, Hui, for that. But that's the second code that we're going to work with here. Okay, so what are we actually doing here? Well, we're going to take 2 modalities. Okay, so we're going to take photos of houses, and we're going to take those photos as one data stream, and then we're going to take a couple of socioeconomic indicators from that region, and it is really easy things like how many living rooms are there, how many bedrooms are there, what's the zip code, and 3 or 4 other key indicators of the particular geographic area. And we're going to mix those 2 data streams to come up with a multimodal prediction in sort of a framework that might be relevant to our social scientists, right? Like, how much does that particular house actually cost, given a couple of key indicators and some pictures of the house. So I don't know whether you knew that, but even from on those cloud services, you can use command line stuff. You can easily get cloned into the house data set and download it. If you connect, like if you have an account on Google and you have a drive there, then you can mount this drive so that you can access data that is in there. That's quite convenient. And then you can simply navigate it using your standard shell commands. So where are we here? We can do that with a percentage sign, the present working directory. You can see what is in there. You will have to cd into the exact folder where all your images are. And then when you are in that dataset folder, the houses dataset folder, you can see that there's a bunch of images in there, right? This is really cool. It's all the frontal kitchen and bathroom images of all those houses that we're going to work with. And it's quite a bit, and it goes on and it goes on. And then take a look at some of those images. So I just picked randomly the image of number 220, and we get a frontal image of that house. I think we get a kitchen image of that house. We also get an image of the bedroom and also an image of the bathroom. Okay, and you will have those images from all the different houses, or in most cases it's so many. Okay, and then we'll write some functions to load the data first. And we have some classic spreadsheet data, right? And in the spreadsheet, yeah, there they are. It's the bedrooms, the number of bedrooms, the number of bathrooms, the area, like a categorical variable, and the zip code, and the price of the house, of course. And we're going to use pandas to read that. I commented here a bit more since it's not as straightforward, but it should be really easy to go through that code and get it on your own. How these functions really work in detail. Feel free to get in touch if you have problems, of course, afterwards. We're going to process the data and reshape it. So it's basically a little bit of juggling of the data around. We're going to transform it a little bit. So that we can work with it in a neural network context. Again, this is 101 deep learning here. So please, if you don't understand that, get in touch, or also check out the other deep learning modules that are online. Then we're going to load. So this was the stuff necessary for handling the spreadsheet data and juggling bedrooms, bathrooms, areas of code and price. And now we want to load the images themselves. And again, I'm commenting it quite in depth here, since it's a bit more elaborate than the stuff that we covered before. But it's still pretty straightforward, just reading data and resizing it a little bit, so that we get the data in a nice format. These are the functions for it, as you can see here, the one for loading the images, and these are functions for processing and loading the attributes from the spreadsheet data. Then we're going to build those two models. And remember, from this easy thing that we did first before the break, okay, that here we had two different kind of inputs, a first branch, a second branch, and then we're combining the branch and adding a fully connected layer as a decision unit or analysis unit. It's exactly the same architecture, but a little bit more complicated and built around proper real data here, okay? So the first thing we want to do is we want to create the network to address the socioeconomic data, so the spreadsheet data, and we're going to define a fairly flat deep neural network with first 8 units, then 4, and then another one if we're regressing as a decision unit. And then we have a convolutional neural network, and this has a bunch of mix between convolutions, then an activation function, a batch normalization in between to get numbers in line, and then a pooling layer. I don't want to go into detail how those convolutional networks work. Again, there's another module on that here, but it's simply the way of how you stack convolutional neural networks. And as you can see, we have here 3 of those convolutional and max pooling layers, and we're going to flatten them out in order to get a first layer here for the convolutional neural network, and do some dropout regularization. All this is really standard convolutional neural network stuff. Okay. So we're now going to construct the data pipeline and actually execute the functions that we wrote. First, we're going to load the attributes from this houses info txt data that is, I think, buried somewhere here. Right? You can see that houses info txt is the last file in one of the data that you downloaded. And we're going to load this data. We're going to load the images, and I'm giving it explicitly the house data set, and we're going to normalize the images to be between 0 and 1, right? Again, this is buried a bit deeper in the idea that neural networks don't like values that are too crazy. Ideally, you want to keep everything between roughly around 0, so that your learning works well and that you don't have vanishing gradients and that sort of distort your model. This is why classically in neural networks, you normalize your data before inputting. With the images, that's fairly easy because we know pixels range all the way up to 200, the value of 255 to give the intensity and the intensity in the different channels. We're going to do a quick and dirty split into only a training and a testing set, right? If we want to do hyperparameter optimization, we would have to have a validation set, of course, as well. But this is really quick and dirty here. So we do a 75-25% split and come up with data for the training attributes, the test attributes, the training images, and the test images. And this is when we take a look at the training and the test attributes, this is the shape. Okay, so we have 271 observations. It's not very much with 5 attributes here for training, and then a test set of 91. And here we're going to extract the maximum price to normalize the price to be between 0 and 1. Again, this helps the neural network to train. And yeah, going to process with this process function that we wrote the training and the test data, and then we're going to build the model. Okay, so we have the MLP and the CNN that we take in. We get a summary of the MLP model, the easy one for the spreadsheet data. We have a CNN model that looks like this. This is the moment where we're going to combine both of them together. We will concatenate the output of the MLP model and the CNN output. We do a analysis unit layer, which is a fully connected deep neural network here with 4 neurons, and then the next layer with 1 final unit. This one has a linear activation function, of course, because we have a regression problem. And then we build the model of it, right? And this is how it looks like. And you can check out the model summary. And this is the whole beauty of it, right? Again, it's basically the same logic as we had here. The first branch, second branch, we combine the branch and we do a fully connected layer. But here it's a little bit more complex to really accommodate the different data structures. We're going to train it, and we're going to add a small learning rate here. We will have a loss function that is the mean absolute percentage error, the MAE, because we have a regression problem that works pretty well. And we're going to run it for 200 epochs. And this running takes about 6 minutes, right? 6 to 7 minutes for 200 epochs. Even on the small sort of compute unit that they in-house provide, it's fairly okay, but you can see that, yeah, it works, but it's not massively well working, right? But it gives you an idea about compute time on the cloud. If you do it locally, I think it should be quite a bit faster. And if you pay them money, of course, get a better compute, and you can do that faster as well. Okay, so this runs and runs and runs and runs. And as you can see, the loss goes down, right? Here goes down, 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 sort of fish. And you get to a range where it's fairly low. We have a small loss here, a bump a bit here. And then we can simply predict using the model, right? You simply call the predict function on the test data from the attributes and the test data from the images. And you get predictions out. That's quite neat. And we're interested in understanding the difference between the predicted house prices and the actual house prices. So we simply calculate it by flattening out the predictions and calculating the percentage difference. We can calculate a mean of this absolute percentage difference and a standard deviation, and then print some results. And we get a mean of 32.71 percentage points here, which is okay-ish, right? And it sort of works. It shows that we get the ballpark figure out. We have quite a high standard deviation overall, which tells us, yeah, that's the first serve on the model. And now you would have to really start doing your hyperparameter optimization like you would typically do with a deep neural network, right? Iterate through different optimizers, learning rates, all these different kind of things, different architectures to get to a point where you are quite happy. Let's wrap our heads around some thoughts about what we did. Okay, so you get typically with a fusion model here, if you play a bit around with the hyperparameters and the optimization in a range where you get between 18% and 24%. So this 32% was, yeah, pretty bad if you compare it to other runs. You can get much higher usually. And that's nice, right? But something you would typically want to do is something called an ablation study. And you find that in a lot of computer science articles when you read them about multimodal learning. Ablation studies are basically studies where you not only do your task that you want to do, so do your prediction task with the fusion model, but you also try it with different individual models on individual modalities to see how much power they have, right? And you will find that just with the deep neural network here, you can get to 22% mean average error, which is lower than the 32 that we have here, of course. And if you only run the CNN, so just the images, you're at 57 percentage points, right? This is, of course, even worse, right? It tells you, well, you get a little bit of a signal, but not much, right? So combining those substreams in an ideal case, you add a little bit of information from the images to your spreadsheet data, but not dramatically a lot, right? So what are the reasons for what is going on here in this context? First, let's think about the number of observations that we actually have. Okay, so remember that we only have about 500 observations, which is not a dramatic amount of observations that you have given the complexity of the task, right? So typically in machine learning, you have many more observations that are coming in. Then the number of variables, of course, is fairly slow, right? It's fairly low, right? We have one outcome variable, which is the price of the house, and then we only have the number of bedrooms and things like that, and a zip code in an area. That's not a lot of information, right? Ideally, you would want to have more information here. Think about the information flow that is going on here, right? So what is the dominant data stream? Clearly, you can see that the dominant data stream here is the spreadsheet data. Okay, you saw that here with when you run the deep neural network alone. This is clearly the dominant data stream. So to check whether your second stream actually has any predictive power on what is going on, you could, of course, resort to a sort of a data science-y solution here and regress the results from one stream on the other to see whether there's any information in there left that actually can be modeled. So is it worth adding this or not, right? And if that is the case, then you can actually dig a bit deeper into tweaking that model a bit around and thinking that through properly. There is stuff to be said about the optimizers, and we'll do that in a second on the slides. Think about your favorite optimizer for a convolutional neural network, for text, for microdata. We know that these like different optimizers, right? Deep neural networks for these tasks. So just one optimizer to do things might favor one of those data streams over the other. And there's different ways in how you would have to address them. We will cover this in the slides a little bit. And in order to fine-tune the model, of course, you can do transfer learning and pre-training of them, and we will also cover that on the slides in a second as well. So this is a first model that shows you how you can do that, and then how you can easily combine those two different strands in order to get to a fusion model that already helps you predict something. I think there's a couple of questions that I'm seeing at the moment. Let me see. So R.K. Goyle says, seems the model developed in this notebook is similar to ensemble learning. And how shall backpropagation take place here? Why don't we pass a combined input to a single model first? That would be more interesting to see, like CNN, which can handle text and data both. So this is actually what we're doing, right? So if we go back here, we are learning together, right? It's not ensemble learning where we have the same data on one model and then all the same data on another model. We have two different data streams, one data stream, another data stream. Then we use a specialized model that can do a really good job for them. So on the image data, we use a convolutional net. On the spreadsheet data, we use a fully connected net. Then add those two representations as embedding structures, basically, and then have a final model. And we're going to learn all parameters for the CNN, for the fully connected, and for the analysis unit all together, okay? So this is one big combined model. And again, in the easier way, it's a bit easier. In the first code, it's a bit easier to see, maybe. You can see that we have one branch that is coming in here, second branch that is coming in here. We concatenate everything, and then we have another dense layer on top, and we learn everything all together, right? It's one big model. And it's not ensemble learning, right? Ensemble learning would be to have all the data in one model, all the data in a second model. They might come up to different conclusions. So we need an aggregation mechanism, which could be a majority voting or another machine learning model to sort of soak everything up. But in those cases, these three learning moments would be separate and not all together. And this is what we're doing here. Are we using the MLP and CNN independently here and finally giving both outputs to a DNN? Yes and no, right? It's independent models, but everything is learned all together. It's one cost function in the end. Okay, you can see that here. So this is the moment where we define the cost function. Here, okay, so we only have final loss, which is the mean absolute percentage error in the end, and we're going to use this Adam optimizer to get there. Okay, so this is where we're getting. Hope this answers your question. Are images also labeled? Yeah, the images are labeled, of course, that correspond to the corresponding observations. Okay. There's another new message. Okay, cool. Sweet. Happy campaign. Cool. So this is very easy code that shows you how easy it is to actually integrate these things and generate a model in a first step that is sort of working, right? And this is exactly where the fun bit comes in, right? It is sort of working. Now, how can we make sure that the stuff is really working? Okay. So far, we said, well, we have these magic embeddings and these magic things. If you just throw them together, like this magic data representation, and add a little bit of AI magic on top, and we don't know how this AI stuff actually works, everything will be magic in the end, and this will just be cool, right? Forever and ever and ever. And the point is, in science, this is not how it works, right? And it won't really work well. In particular, since, and we talked a lot about that this morning, multimodal data is really complex, right? It has a couple of challenges. It's heterogeneous, very different, the modalities. They are connected in one way or the other at different levels, right? High semantic levels or actually quite low just correlation levels. And they may be interacting in all different kind of ways, those modalities. This is really challenging. And as a politician, as a German politician recently said, like problems are thorny opportunities, basically, right? So even though it's a challenge, it's also an opportunity. And as scientists who like to think about complex problems, we can derive information from that and bake this information into models, right? We can write better models on the basis of our understanding of the problem. And improve upon those models in a clever way so that we can get to better predictions. And the way how to improve our thinking about those models, this is exactly what we're going to do for the rest of the afternoon. Okay, so we will cover a couple of points in how we can sort of better bake those embeddings together in more clever ways, and also into how we can better align our data streams together so that models have it a bit easier in the way in which they analyze the data in the end. Yeah. Let's go back to the slides. Let's have a step back and think in a careful way about learning and optimization, okay? So learning and optimization. What we are doing with those optimizers is, when we train our models, is we try to find areas that are really on the top of these mountains, okay? Because we want to optimize things. And the way to judge whether we are on the top of things is to simply walk up there and then see whether it's going very steep. And if it's steep, that's good, because we gain a lot of knowledge. And if it's flat, after a while, we know that we are on the top, and that's an area where we want to be at, right? And we can have different ways of building optimizers that work in that way. Yeah, and of course, if you go up or down, that's just a mathematical problem, right? We invert everything with -1, and then you just have to look for the bottom here. But again, I don't want to confuse you here, right? What we're doing in optimization is we're trying to find the top of something, right? Like a peak. With these different optimizers, we can walk through this landscape and take different probes at where we are and update the model parameters accordingly so that we get to a point where our cost function actually does the stuff that we hope that we want it to do, right? We want it to be close to a certain result, and this is the way how we write up our cost functions in different ways in deep learning. And when we optimize this, multimodal analysis has some extra and some particular challenges that that may come with this. So the first challenge is, as we mentioned already, the data is from different sources. These different sources mean that the data comes in different subgraphs, right? And talked about this a couple of times now, that data is coming in different subgraphs in our network, depending on the type where they are. And the problem is that these different data types might have different preferences for optimizers, right? For some optimizers, like some data requires some optimizers and other data requires other optimizers. And we know from deep learning, from doing it practically, that, for example, a convolutional neural network, they quite like high decaying learning rates, right? Where you have a boost in the beginning, and then this goes down, and then everything sort of settles, right? You think of a neural network that you shake very strongly and then just a little bit, so that we only fine tune afterwards. Recurrent neural networks, like adaptive methods throughout, and like in particular stochastic gradient descent methods. But this might be something completely different than a CNN likes. Okay, like deep neural networks, fully connected, like only adaptive methods, they don't care so much for the particular optimizer. But the problem is, if you want to combine a CNN with an RNN and a DNN, I mean, just the question of learning rates might give you problems, or an optimizer works well for the DNN part, but not so well for the recurrent part, or the other way around. And it's really challenging to learn everything at once in the way I just showed you in that code, right? This is one of the reasons why this code isn't just super great, and you cannot just throw a halfway solid fusion model at some code, but why you really need to sit down and think through what you're doing. Okay, and if you take a look, quick side note here. If you take a look at the computer science literature, this is how the fusion literature developed a little bit over the last, 10 years or so, right? At first, people were using these early like fusion paradigms from back then and building models, soon finding out that, well, this doesn't really work super great. Where can we tweak things so that the learning works better? There are two solutions that we can do here. So we can we can do pre-training, okay, and we can train each model separately, and then assemble and fine-tune. So learning would occur first in the CNN part, and then in the part where we have the socioeconomic data, and then we're going to combine those results according to the labels, of course, in the right order, and then finally do them. That's one way of doing it, of course, right? This would allow us to basically do some kind of assemble and then fine-tune the whole thing in the end, then have and then do that in the end. The problem is, if you want to do the final training exercise, adaptive methods like Adam are not super great, because you have all these pre-tuned models already that you put in and then assemble and then just fine-tune in another go with all the data. And if you take an adaptive method to do all that kind of stuff, it will basically break all your weights in the fine pre-trained models. Okay, so that doesn't really work, right? So one solution is train each of those strands separately, then combine them, and then fine-tune them with a very, very small learning rate. This could work. If you really choose a fine grained learning rate at the very end. Okay. Examples for that could be a sentiment with images, like try to predict a sentiment from images and captions. Okay, so you can train a CNN and an RNN separately on sentiment on your particular data set. Right? You generate visual and verbal representations on the basis of these two, and then train your DNN with representations on the sentiment. So you have 3 pre-trained modules. You then stick them all together, and again, with your whole data, you fine-tune them all on the same segment. Okay, and of course, when you stream data, and I think this answers R.K. Goyle's question in the chat. You have to make sure that in your batches need to be appropriate, right? You can't just mix a random observation for one image with a random observation from another text. They all need to go through with the same batches so that they actually meet the same target information, the same dependent variable at the very end. But this is one way of how you could sort of build up slowly a fusion model where you do a specialized learning in one module, a specialized learning in the second, you get embeddings through, and then you do a specialized learning on your analysis unit in the end. This gives you pre-trained modules on each of the 3 modules. And then you stick everything together, all those weights, you keep them, right? And then you do another pass with your whole information and really tweak this only very, very ever so slightly, okay? So make sure, of course, and I hope this addresses R.K. Goyle, right? We check the code quite a number of times. You do the mixing in the end, right? In those stages where we go back here, okay? Let me show it here, because here it's really easy to see. You have one branch that goes in here, okay? And this is the branch that you would want to pre-train on your first part of the data, like the image data. And then the second branch that you would go through with, I don't know, maybe other data, the text data. And you would train them separately on your code. And then combine those two with just the concatenated embeddings that you get from piping stuff forward. And then train this one in a separate way. Okay, so you have 3 separately trained models. And then you can generate one big model, the big one that we are generating here, and train it with a really small learning rate in the very end. Okay, to give you the same picture here for this other code, we have the MLP, right? You could pre-train that with just the socioeconomic data. You could have the CNN with just the image data. And you pipe the information through and get embeddings out of that. And with this embedding information that you concatenate in this concatenating way, you would calculate a combine of everything and pre-train this guy here. Okay. And then in order to fine-tune things, what you would do is, since you have really used different ideal optimizers for all these 3 different modules, you take a last optimizer, and that ideally is something non-adaptive, like a stochastic gradient descent or something, where you don't have adaptive learning rates or like adaptive momentums, and really have a very small learning rate. And by having this one combined model, right, where you combine the input from the MLP and the CNN and build this large combined model, you really fine-tune everything and learn everything then in a fine-tuned way at last, right? And the small learning rate makes that all the weights and all the biases really get jiggled around a little bit, not too much, to really fine-tune everything on the ensemble learning, and then on the joint learning. And this then actually helps you make this. Okay. I hope this helps archaic oil. Another solution, because we want to get around the problem that we need different optimizers for different things here. Come on. Is to do transfer learning. Okay. And so what we did right now is we pre-trained our CNN and our recurrent neural network, for example, or another deep learning network, like for the 2 strands, the specialized networks, on the basis of our data. But instead of training this on purpose on our data, we could also build on existing pre-trained models that have been trained on, I don't know, millions of images or vast corpora of text, right? It could be a language model instead of a recurrent neural network. It could be a VGG instead for a CNN, and get that information, and then, of course, not retrain those 2 modules, but then really train the deep neural network that you have in the end as your final decision unit. Train this layer by layer to really slowly ease in the information and freeze the others through that process. And this already might help you to wrap your head around or get around this optimization problem, because you have pre-trained models already that you stick in there that don't require an appropriate optimizer. You just get the embeddings out. And then you just need only to train the deep neural network in the end. And by doing the layer by layer, this might actually help you. Okay. So what did we talk about here? Well, we talked about how challenging it is to actually train a model, a fusion model, simply because of the fact that the different branches that have specialized neural networks might require different optimization methods, right? Some like momentum, others don't. Some like particular kind of optimizers, some like particular kind of learning rates. And by chopping up your problem into different learning phases, you might be able to get around the fact that these different elements require different kind of optimizers. Okay, this is what we covered. Let's see whether there are any questions. Okay. Cool. I can't see any questions. I think Archie Goyle is happy now as well. So we managed to wrap our head all together, I think, around these things. Okay. Keep your questions coming, guys. This is really useful, okay? Because I'm talking into the void here. I can only see whether my pace is all right, my explanations are going the right way if you keep asking me questions. So please keep them coming, and I'll do my best in order to answer your questions, okay? So that was a first way of getting around this. And let me just quickly see whether we want to break. Yeah, let's have a quick 5-minute break here. And then we talk about how we can fuse and coordinate the representations and how this might actually help. So let's meet at 1:19 on your end, okay?
think you're still muted, Chris.
Here we go. Another lesson I learned from the pandemic, Sarah, that when I participated in workshops like this, these 5-minute breaks, they actually, since you spend so much time in front of the screen, it makes a big difference for attention and focus, in particular over a bit of a longer time, like a 4 hours period that we're facing today. So yeah, great to see that it works out for you. This is really cool. Okay, let's let's write. And we will talk about, so what have we talked about in the last sprint, like the first afternoon sprint out of 3? We talked about learning and optimization, right? I showed you some code, how actually easy it is to use some code and then fuse those embeddings together, or concatenate those embeddings together. And after first hooray, this is working, we're like, nah, not really working. So why would that not be the case, right? And one of the first obstacles that we encountered was maybe the optimization works different for different parts of, like, subcomponents of our graph, right? Because one has a convolutional net, the other one a recurrent net, and they like different kind of optimization methods. So we need to wrap our heads around what's going on there, if we want to do real good optimization, of course. Now, let's go and check out some other clever ways in how we can think about these things. So the first thing that we looked at was the architecture, right, of the whole model and the optimization of the architecture. Now, the next thing is the data, right? Maybe there is something about those representations that we can actually do, right? Remember that at the moment, the only thing we did was simply concatenating them, so stacking them on top of each other. Maybe there is a more clever way in which we can add this information together and instead of just stacking it up on top of each other. And the way how we can think about this is called fusion, and this is the nature of this particular sprint. We'll talk a bit more in depth about how to fuse the information and the embeddings. Let me share my screen again. And please keep your questions coming, right? They're all really good. So this is the only way of me getting any kind of feedback from you guys, okay? And really understanding whether this is working well for you or not. Come on. Cool. Okay, let's talk about representation fusion. As proper scientists, we like to start with the definition. What is fusion actually, right? So fusion is a joint representation that models cross-modal interactions between individual elements of different modalities. So far we were concatenating the information, but maybe we want the information in those embeddings to interact with each other in clever ways, right? And then bring them together in some sort of way. Fusing modalities is a continuum, right? If you think about this in conceptual terms, imagine you have 2 cameras which take a look at the same thing. The information is quite similar, right? It is quite homogeneous that you get from those 2 sensors. However, if you have an image and some text that goes along with it, it's way more heterogeneous, and you have to think way more carefully about the way in which you want to fuse those different data streams. It's a continuum here again, right? There's no black or white if you think about multimodality. Again, all these challenges, as we learned, are just opportunities, and our way of modeling and addressing them might help us out here. So what is the challenge actually if we think about fusion? So we have information that's coming from the image, and just for the sake of this example, we're going to make it blue. And this information is coming through an encoder like a pre-trained CNN, for example, and generates us an embedding. And we also have an embedding that is coming in a text format, and we're going to pipe it through some recurrent model or even an attention-based model, like you've learned with Moritz Lauer a couple of days ago. And we get an embedding out. And instead of just stacking them on top of each other, we want to fuse them, right? So that we want to have an embedding that has the same length. So if this is 200 and this is 200, we now want to have an embedding that's 200 long as well. But it mixes both pieces of information, and ideally in a way that really helps us solve our task, right? That's really the challenge here. So how can we think about these things? Let's build this up properly, and let's approach it. And again, this is me assuming that you guys are all social scientists in one way or the other, from sort of a regression way of thinking about this. Okay, and let's think about a univariate case where we only have one variable. And we have a modality A with one variable and modality B with one variable, and we want to fuse it. And there are different ways in how we could do it. Okay, so we could simply add it, and we can have a weight for modality 1 and a weight for modality 2, and maybe model an error term and have a Z that is coming out of it, right? That could be simply an additive interaction, right? You have one embedding, stack another embedding on top, and simply add each of those elements. Instead of adding, why not multiplying it, right? We can also multiply those two modalities and do that here, right? We have one variable here, another variable here. So multiplying it, it really helps us out. This is really straightforward in regression framework. And everybody who has done the 101 in econometrics knows that ideally you put both of them together, right? Because then you have an additive way of adding information and a multiplicative one, okay? So you get both of them at a time, and you need that for an unbiased estimate. So we've all learned that this is a good way of sort of fusing information from two variables that might come in and that might be from different modalities on the same object Z, right? That's really cool, and that's a regression framework of fusing. Let's take the next step and take this from a univariate case to a multivariate case. Okay, so we have modality A, modality B. Now they come with different variables, and one way of adding them up could simply be addition again, right? Really straightforward. But we could also multiply them, right? And have each of them multiplied with one another at these stages. And if we can multiply them here, then why do we actually have to multiply those two together and in pairs? Why can't we do a bilinear fusion? Okay, and this makes sense if we sort of lose a bit our regression framework, but think more in the terms of embeddings here, right? So you could, for example, you could, for example, take all values in here and multiply them with this value, and then this value, and then this value, and then this value of the other embedding. Okay, you can do that for the second one, and also for the third one, right? And that's a really flexible way because you have two embeddings, one 200 long vector and another 200 long vector. And instead of simply adding embedding like spot number 1 with spot number 2, spot number 3 with spot number 3, and so on, you do that with each possible combination, and you end up with a matrix that is a multiplicative matrix, right? And this makes sure that you really cover all of the possible ways of interacting these things, and that gives you really powerful sort of embedding representation that fuses these two embeddings in all kind of possible ways that you could think about it. But is it really, right? This is a paper that came out in 2017, which said, well, you know what? We only so far had a look at multiplicative ways of doing this matrix. Something we did not do yet was simply like have this additive component to it, right? And for that, we need to add a 1 at the end of each of the embeddings. So instead of having a 200 embedding vector, it's a 201 embedding, and the last digit is 1. And then we're going to multiply this 1 here, which gives us this blue line, and vice versa, the red line. And the way this is combined then is by combining this not only as a multiplicative way, but also in an additive way, right? And think back to this line, right? We as social scientists, we know this line, right? This is our home turf, right? Interaction effects. We all know interaction effects. So these guys basically did interaction effects like we know it in econometrics or statistics, and did that for embeddings, right? And then said, well, let's do that for embeddings. And this is, I think, yeah, I don't know, as a social scientist working at the intersection to computer science, this is really easy, guys, right? I mean, you yourself could have come up with that idea with some basic econometric training that, of course, this is a way how you would fuse embeddings, right? By having not only the multiplicative element, but we all know that it will give you biased results if you don't also have an additive component to it. And instead, it was computer scientists who did that, right? But this is, I don't know, I'm just pointing out that not everything has to be rocket science, right? These can be really easy ideas that in the end will have really powerful impact and work really, really well. And why do they work well? Because you understand what's going on there mathematically and are able to express that in mathematical terms in the end, okay? So a really cool way in how you could fuse that information all together by having interactive effects between each component in your embedding, and also adding an additive component to it. Really cool. So instead of simply concatenating those two vectors and hope for the best, you're actually making a rich, dense tensor out of that that you can then hand over to your deep neural network and let it work on that tensor here. Okay. Cool. So multivariate fusion. This is representation fusion. One way of thinking about these things. I think there are a couple of questions by now. Let me check. What could be other ways of conceiving interaction apart from including additive or multiplicative terms, multiply image and text data? Yeah, see, this is exactly what we're doing, right? We are having the embedding from image and the embedding from text that is going on. And we are multiplying it here, right? In all different possible ways, in all ways that are imaginable, right? Each single cell of the embedding is multiplied with each single cell of the other. So we're covering all the multiplications. And on top of that, by adding a 1 here and a 1 there, we're going to also cover the additive component to it. So you are covered, my friend. This is mixing all the information in all different ways possible. Okay, make sense? Seems so. Cool. Other questions? I have some personal questions. I'm gonna address them later, but like joint questions for everybody else. Okay, then let's keep on rocking, guys. So we learned how we can fuse this information. Now let's think about representation coordination a bit better. Again, let's start with the definition. So far, we were simply throwing everything together and mixing, right, with multiplication and addition, and we're mixing the pot and then hoping for the best. Let's think again once more, a bit more carefully about what is it that we're actually doing here, okay? We want to coordinate our information maybe in different ways, okay? It could be that we want to have some kind of strong coordination. And you can see here that the red and the blue mix fairly well. And we can also have some partial coordination where the red remains dominant, but it just gets a hint of blue up there, and the other way around, right? So there may be different ways of bringing those two together. Okay, let's think about this a bit more closely and how we can make use of that for coordinating those representations in a clever way. So we have two modalities that we want to coordinate, and we have an encoder, aka a neural network, a pre-trained neural network, for example. It is some function A and some function B where we pipe our data through. And ideally, we want to coordinate it. And it's obvious, right, that we need to have a function G that takes ZA and ZB and then gives you a coordinated version of these, right? That's the goal. So what can we use as a function here? So you've probably, like, if you've played around with word embeddings, you know that cosine similarity works fairly well, right? If you have one vector, and then you can easily calculate the cosine similarity to another vector, and this will give you sort of similar results, and you know that you're in sort of roughly the same area in this high dimensional space, and that means that your word is fairly similar and almost the same, right? Really easy. Another way of doing things is through canonical correlation analysis. This is something that people do in statistics as well. It's basically telling you how, like it imagines two data sets, right? AKA two sets of embeddings. And then we want to find projections that are most similar in one and the other one, right? So it's basically two spaces to imagine, for example, text embeddings in one language and text embeddings in another language, and they all live in 200-dimensional space. And ideally, you want to get them together in a way that king maps to king and queen maps to queen in those two different languages, right? And you find a way in doing that, and you can use canonical correlation analysis to do that. Now, something really cool is a really cool thing how we can coordinate these two embedding spaces is through autoencoders. Okay, and let's tackle deep canonically correlated autoencoders as a sort of an architecture how you can coordinate those two embedding spaces really well. So how do autoencoders work? Let's start with this one. And you can see an autoencoder here on the left and an autoencoder on the right. And what autoencoders do is they work like a funnel. Okay, you start with data, and then you narrow your neural network really, really down so that you get an abstract representation. And then you open it up again, and you train it basically on itself so that it helps you represent in the very end your complex data in a really short and abbreviated abstract way, right? And this is the stuff that you actually want to do. And if you do that well, it can be yet another way of generating a embedding for a particular text, for example. This is really cool. And you can do the same thing for images, okay? But remember, the goal of the exercise is we want to coordinate the fusion, right? We want to have embedding spaces for text and images that are informed by each other, okay? And how could we do that, right? Well, why don't we here in this abstract space at the center of those two funnels of the text and also the funnel of the image data, sorry, why don't we just add a canonical correlation analysis in here, right? That will sort of help project the text embeddings to the image embeddings. And of course, they must not be the same necessarily, but they don't need to be the same necessarily, but ideally they are close, right? They are close in this high dimensional space, and we simply use a canonical correlation, CCA for that here, and then simply stick it in, and then have a cost function that consists of three components, right? We have, as usually in an autoencoder, this part here, we have this part here, and we have a third part of the cost function, of the joint cost function, which is the canonical correlation analysis. And then we can train them all together, right? And this is a really clever and intuitive way, I think, of coordinating those embedding spaces from the images and the texts, right? Or for that matter, for French and German, or other two languages, or I don't know, different kinds of corpora that might come up, or that might come to your mind. And this is a really good way of how you don't fuse them by multiplying them together, but you inform them, right? They get close, like they get similar, but not 100% the same, right? And that's a really cool architecture to do that. I think this is really powerful. This is really, really cool. Some intuition. Why is it actually useful to have a coordinated embedding space? Well, think of multimodal data as sort of multiple views on the same object. So in computer vision, right, like you're only seeing my face here, right, through this one particular camera. If you had another camera in the back, you could see the back of my head, and this would give you a much more complete picture of Chris's head, right? And this would be multimodal data, and what you're seeing is the same thing, right? So you want to have an intact representation in an abstract embedding space, of course, of the one thing that's all together. And this is how it works here, right? And this is how we bring everything together. So each of these individual views are part observations. They're of course correct, right, for their individual sensor, but they only give you a part of the reality. Okay, and this is why you can why their coordination might make sense, because then you can easily translate between those spaces. Something that was used here in this context fairly early on is an application. It's basically like you can use it as a search machine, right? A query machine, where you take a picture and you tell it in words, well, subtract day and add night, and you find similar pictures that are close to it here. Okay. Really, really straightforward and early application of this already. Okay, so what did we cover? We had a look at the representations now in order to tackle multimodal learning. And the representations, instead of just concatenating them, why don't you fuse them in different kind of ways, right? In multiplication and additive ways. That's one way, like throwing everything together into one big pot. Or if you want to be a bit more subtle, you can also do that by informing them, right? By coordinating them in clever ways. And this deep, I forgot the name, deep canonically correlated audio encoder is one way of doing it. There are others, of course, but this is one way of deep learning architecture and how you can do that. Okay, I can't see any questions at the moment. Let's take a quick 5-minute break, and then we are here for the last sprint. And the last sprint will be on alignment, okay? And then see you then. Welcome, welcome. This is the last sprint, folks. Amazing. You made it almost through the whole workshop, almost. So what did we do in the last sprint? Well, we covered a clever way of how we can bring together those embeddings, right? Those embeddings are high-level abstract representation of some kind of meaning of what is going on there. That might help us in infusing or coordinating those embeddings. This is really cool. So let's take a look at the last element of a last thing that we can do to overcome those challenges that are embedded in multimodal data. And this last thing has to do with alignment. And let me share my screen again for this last thing. Okay, this is the last bit. As before, keep your questions coming. They're all great, okay? And here we go, alignment. Now I can see your questions in live. So I went a bit back and forth. Okay, let's take those last 25 minutes to take a proper look at alignment and to have some last question round then. What is happening with alignment? What does it mean? Well, again, we start with the definition. So the idea is to find relationships and correspondences between subcomponents of instances from two or more modalities, right? This is the formal definition of that. And I'll show you in a bit what I mean by that. It's basically the idea is that we want to connect different things that are going on in our data streams. Okay, so think of that's the idea, right? So you want in the text data stream there is a word and it belongs to that part of the image, and this part of the sentence belongs to that part of the image, and we have others, that third element of the sentence that belongs to the third part of the image, right, and so on. That's the basic idea, the basic intuition in what is going on. And we can have two different kinds of alignment that we're doing. First, we can have explicit alignment, okay? And in explicit alignment, in the explicit alignment models, the alignment is the task of the model itself, right? So you have a deep learning model that really wants to do explicit alignment because you want to explicitly align one element in one modality to another modality in the other. Okay, so for example, transcription software, and if I see this correctly, there is a transcription software listening in here, which is transcribing stuff for somebody else automatically. So hello there, if you ever read us. What it does basically is it identifies on the basis of an algorithm each particular word, right? Governments have made policy decisions, right? It then records when, at which millisecond each word is beginning. And this can then help us to chop the audio file that comes along with it and really identify the audio file that belongs to each individual word, right? And that is an explicit way of aligning things, right? You explicitly align the word here to the audio stream here, right? One way of alignment. Another way is to align text with images, right? And for example, you can have different players and you want to box those players, and you want to have a guy in yellow dribbling ball, like this part of the sentence really aligned to what you see here in the image. And the purpose of such a trained model that does that is you simply show it an image and it automatically pops out a description of it, right? Really, really handy for some applications in computer science. That's explicit alignment. So if there is explicit alignment, there also must be implicit alignment, of course. And implicit alignment is alignment as an intermediate step in sort of a larger model. And you want to align different elements of your data in the different modalities so that you can fulfill a task later on much better. Because sort of you point the substrand of your one model to the substrand in another model, and this is a way of how you can sort of make most of the data, right? Again, right, this boxing problem that we might have here, you might have certain image fragments that you want to sort of point to the correct part of a sentence in order to then finally do a really well done job in sentiment analysis. That's one way of doing things. We might want to detect areas where we can find, I don't know, a kite, for example, and you can see that the model does that fairly well, or what season is related to that image, and you can see that the model takes those fallen leaves as information. These are all applications that you can do in sort of a computer science world. So RK Goyle is asking what an embedding is. We covered that in the very beginning of today's session, if you want to go back in the slides. And I think an intuitive way of understanding that is this with this Barty-Wack idea, right? It is built on the idea that we see things on the basis of we understand things on the basis of its surroundings, and then we can build models that use this information in order to come up with high-level representations, right? That's sort of the intuition for embeddings. It has a latent capture of meaning in there. And if you want to shortcut it, basically, if you pipe an image through a pre-learned architecture like a convolutional neural net, you can get a embedding out of that, like a 100 long vector that in a very abstract sense represents that image. We as humans don't understand it, but that's sort of the outcome of it. I hope that sort of roughly covers the idea of the embedding, right? Feel free to go back in the recording later on, and then of course feel free to get in touch with an email if you need more pointers to literature so you can understand. So by coordinating them and fusing them, you can get far. But here we want to align the stuff, right? You want to align the data to do our task well. And again, as a political scientist, how do political scientists align? Well, political scientists who work on multimodal data don't align too much, right? So there are basically two camps. So one align at a global level, which means they take a whole speech or a whole image or whatever. So there's a Ditchik et al. Paper that takes a look at verbal contribution levels overall. This is speech level. Here's another from Ollie Rittman on speech level. There's one on from Parr et al. On TV campaign ads that recently came out. This is really taking the whole chunks of data, so to speak. And then there's other stuff that takes a look at intervals of time, right? Well, let's just take a 1 minute interval, a 2 seconds interval, a 1 second interval, a 25 milliseconds interval, right? It's fairly arbitrary, right? Because if you take a smaller interval, of course, this gives you more data, but you might chop up a sentence or a word or whatever is going on there. That's problematic because we know there is more information in that data, and that we could get out of it. And apologies for featuring own work that we are currently working on. PhD student of mine, Andy Kupfer, and myself, where we take a look at alignment properly and see what we can do with alignment if you think carefully about alignment and do that in a political science context, right? What's the big advantage of doing alignment in political science? And this is why I have this working paper there. And this is not about featuring myself, but about this work, right? Which is trying to show you folks, okay, if you what can you gain as a social scientist if you do this kind of work well and think carefully about the problems that we want to solve as social scientists? So let's first think about what alignment actually means, okay? So alignment, of course, means that you bring labels together, right? In an image, you have a ball and you have a woman who is, and you have a woman and you want to identify the ball and you want to identify the woman who is playing that ball, and then you want to have it correspond to some text where you describe the image, and you have a woman and a ball, and you find those same things in a word, in a sentence, okay? So the labels that are in there, they're actual, like it's some kind of annotating this data in a way that we as humans make sense of it, right? To a machine, there is no meaning in ball and woman, right? Be it in a word representation or an image representation. It's a geometrical object or a particular sound, but we need to tell that this data and sound corresponds to this shape in the image. And this is a way of annotating things on the basis of labels, right? So this is one way in which our understanding of the idea of a player and a ball come together, right? In addition, we also model things in a way, right? So we generate, we write models in a way that makes sense against the backdrop of how we are understanding those concepts, right? And how we can bring them together. And our model also helps us enter information from sort of the human realm into the data and machine realm, right? It's a way of annotating data because we bring information from one data stream together to the other one, right? We either directly via labels tell whether this is the sound ball and this is the geometric shape called a ball, and see these two correspond to one another. That's annotating data. Or we also embed that information in the model by writing it in a particular way so that these can actually be mapped to get onto one each other. And then alignment really helps us address all these three different challenges that we identified in multimodal data right in the beginning, a couple of hours ago. Okay, so multimodal data is heterogeneous. Yeah, that's okay. If we align data, it might actually help us with the data quality that we have, right? A sensor might be blurry in sort of the visual component, but there might be a really clear sound signal, right? It might be that for a particular task, one part of the model helps understand what is going on in the other one. And by aligning the informations, the model much better learns what corresponds to what in the respective modalities, right? In the respective data streams. So what we can expect here is, if we do that right alignment, is an overall performance improvement, because we much better know what parts in which data stream correspond to what parts in the other data stream. First advantage. Second one is the connectedness of data. Well, you know, we know that multimodal data is connected first at a basic correlation level, but also at a deeper, sort of more deeper understanding of what these different elements mean, right? Remember the wink of the eye that we used. So if we really define what belongs where, we can formulate cross-modal queries. Okay, if we align audio data with a transcription, right? If we know where a word begins and where a word ends, we can extract the corresponding audio stream of each of the words, right? If we know where a player is in the image and we want to look for player instead of, I don't know, goal or tree or anything, we can have the bounding box get back to us and formulate cross-modal queries, which is really cool. And lastly, we know that multimodal data is interacting. And this really can help us in model interpretability and the way how models actually work, those black box deep learning models, and help us develop human understanding of model interpretability. Okay, so what I'll do now is, since this is work in progress, I'll show you a quick example for this part and a quick example for that part, what you can do if you align data properly. Let's go and dive into it. So the first one is to use alignment to improve predictions. And what we use is the political ads from the 2020 US presidential race. We use the Maslane Media Project, and the dependent variable that we want to predict is how positive or negative is the ad. Okay, and we do alignment here, implicit alignment, with a cross-modal attention. So if you've been to Morris class and transformers, we don't only use a transformer within one modality, we also use a transformer that spans across modalities, right? So that the model itself learns which part of the, for example, audio stream is best for combination with a video stream, so that in the end you solve a particular task. We generate features for each of the modalities, text features, video features, and audio features, and then run a model. And these are our results. And what you can see is that if you run audio only for your prediction, you get 82, F1 score of 82. Vision only is 82 as well. Text only is roughly 93. If you mix all them together in sort of an early fusion setup, you get roughly 92, which is close to text only. But if you use also cross alignment with this attention architecture, then you get it to 95, right? And even though this might seem small, right, remember that up in that area, if you think of accuracy terms instead of F1 terms, but like a 0.9 accuracy means that for a user every 10th example is wrong, right? But up here at 95, it's only every 20th example that is wrong, right? And that's, for a user experience, that's quite a big difference here, right? So getting up to that 95 from, I don't know, 90, 92 or 93, that's actually an improvement, and it really makes itself felt in the user experience up here. So that's one way of how you can improve your predictions in the very end for something that you want to do. And another one is alignment for cross-modal queries. Okay, for that we use the speeches from the 19th German Bundestag. We scrape them, and we identify the videos with the speaker on the basis of the lettering of the podium. So we take a look at these people. And then we do explicit alignment. First, we transcribe at a word level using WhisperX. So we know what audio and video segment belongs to what kind of word. That's really cool for chopping up the speeches and identifying them. And then we also analyze the gaze of the speaker, right? So we know there through a model, 6D RepNet, where people are looking. Okay, and if you know where the speaker is looking, you know when they talk to the extreme factions of the Bundestag, right? When do they speak to the left? When do they speak to the right? And you can also tell from the audio track whether somebody is raising their voice to really make a point, to be really upset, or whether they are actually talking in a quite relaxed mode. Okay, so you can take a look at the pitch of the speakers. And what do we find for speakers for each faction in the German Bundestag when they talk to the extreme? Okay, and this is like extreme parties, and this is what we find. Okay, so this is the pitch when members of party look at Die Linke. And of course, this is under control for individuals and male and female voices. So we want to see whether looking at the left party changes the pitch of the voice. Okay, and if the left talks to their own faction and looks at their own faction, there is no change. The SPD not as well. The Greens are more relaxed when they talk to the left, actually, but the Conservatives, the Liberals, and in particular the AfD are much more upset when they talk to the left party. Right? This is what we get, and we do the same for the AfD, for the right-wing party, and we see that the three left parties are really upset when they talk to the AfD, when they talk to them. And the Conservatives and the Liberals are a bit more upset, statistically significantly more upset, but the AfD itself, when they talk to their own party, they're not more upset than talking to other parties. Okay, so this is not a big theoretical insight, but you expected that, right? But the big point is that we want to make here is, hey, guys, if we do proper alignment, see, you can formulate cross-modal queries and do something really cool that will help you in analysis further down the road. Okay, so apologies for featuring myself here, but I thought it's simply good, a working paper with nice examples for the purpose of what we're doing here to understanding these things. Okay, there is a proper big blown, really working code that is left here that you could take a look at. It's the multimodal entailment problem, where you have social media posts that might contradict each other or not. And there's a really nice baseline model that they showed on Keras in order to tackle that. So this is multimodal. It's solving a challenging social media problem. Go and check it out. It's really cool. And I would have gone over it if we had a bit more time. It's all up there. It's really well described. So you should be able to tackle that on your own, I guess. Are there any other questions here in this chat that you guys want to talk about? So is there stuff that you haven't properly wrapped your head around? So Archigoil, the ideas of embeddings, maybe think of it as an abstract representation of meaning, right? I think that's the best way of how you can think about that. And then there are different ways in how you can get to this abstract representation of meaning. The idea, like the way how this is informed, is on the basis of closeness, right? And that's the Bardywalk example, and how close, like you understand the meaning of something given the context. And that holds for images, it holds for text. That's sort of the underlying hypothesis here. Oh yeah, material, of course. Yeah, of course. Let's go over that. Quick, cool. So this year, a couple of really good summaries came out that walk you through some foundations. I'm putting those readings up here because I quite like each of them. They're at different levels of complexity, and I hope each of them sort of gives you a nice start, and it's pitched at different levels of complexity. Check them out. Of course, as always, there's the one and only Bible from Ian Goodfellow on deep learning. That's a book you always should work through. This is always a good start here that helps you with multimodality. This is internet resources. I quite like LP Morenzi's stuff. So we had 2 great workshops last year. There's also a really proper multimodal machine learning course that you can study. This is really good stuff. I learned a lot from his stuff. Yeah, and if you are working with deep learning, get in touch, right? I'm always curious to see what you guys are up to. Always feel free to get in touch, and that really helps. Okay. There's a question from Sven. If one is starting from pre-trained single modality models from Hugging Face, how would one decide on how to combine them into multimodal model? Well, it depends, right? You can simply do early fusion and generate an embedding out of your pre-trained model, and then fuse that or concatenate that in different ways, and then train a joint decision maker that combines those embeddings. Or you already have the Hugging Face model come up with a decision and simply aggregate those decisions together. These are basically, in a rough nutshell, those 2 basic ways. Yeah, and I think this is it, guys. As I said, feel free to get in touch in case you want to know more. Feel free to get in touch with all your successes, of course, right? Not only your problems. I like to read about successes you have as well. And I hope you're enjoyed about and excited about multimodal learning. I surely am. And hope to meet you at some point virtually or even on a conference or a workshop in a face-to-face setting, always feel free to get in touch in whatever format. And thanks for being here. I hope this was enjoyable and informative, and looking forward to being in touch, guys.